very good morning to one and all present here. With immense pleasure and great honor, that I, Dr. Arastro Bandhopadhyay, welcome you all to the session 8 of day 3 of our oncology program. Today we are privileged to have with us a pioneer in the field of medical image processing, Dr. Debdoot Sheet, sir, Associate Professor at the Department of Electrical Engineering, IIT Kharagpur. Now I'd like to share with you the brief of the session. Artificial intelligence is a commonized term which is so frequently used to sales and marketing pitch of any commodity in today's world that it has created more misconception and myths which hide the reality under its grasp. Those of us who have been working in the field and its applications to healthcare have been taking small and impactful steps in accelerating quality of care delivery in such each stage. The talk by Sir will focus on contribution of our group to 3 such stages of oncology care delivery, from accelerating detection to enable large-scale evidence-based diagnosis to effective and accelerated therapy planning from pre-interventional imaging. The presentation will be heavy on mathematical concepts in an effort to not hide its true self under the wrap of fancy highlighted terms and flashy presentation. The equations will be kept to a minimum to keep it engaging. So now I kindly request our esteemed Principal Sir, Professor Dr. Zubasish Saukas Sir of SIMT, our coordinator Madam, Professor Dr. Moshmi Atto Madam, our co-coordinator Madam, Professor Uttara Basu Madam, and our most very welcome Professor Sharon Ghosh Sir to come forward and felicitate Sir with Uttoyu and memento. So please welcome them with a round of applause. Science service felicitating Sir with the our co-coordinator Madam is felicitating Sir with badge. Has been felicitated with memento. I'd like to call our principal sir, Professor Dr. Zubasish Saukas Sir, SIMT, to welcome sir.
Very good morning to one and all present here, and especially resource person of today's session, Dr. Debdoot Sheet. Sincere thanks and gratitude on behalf of Supreme Knowledge Foundation for accepting our request in spite of extremely busy schedule. Although I do not share the personal things, but I'd like to share. I have received his last mail around at last night 11:47 precisely, and he has started his journey at 5 morning today. So this is the busy schedule he is having. In spite of that, as he's having a session at 9:30, So I was in a, like that was my concern, whether from Kharagpur directly he is coming. So we have offered our like guest house support, but he told he is very busy with some of the projects of different countries, multinational projects. So, and he told, like Professor Sarkar, you do not need to worry, I will reach much before your session. So thank you again for, that is also great learning for all of us, and I'm sure we are looking forward to a great session. Thank you once again.
Thank you, sir. Now let me share the bio of Debdoot Sheet, sir, with all of you. Debdoot Sheet, sir, is an associate professor in electrical engineering at the IIT Kharagpur. He received the MS and PhD degree from IIT Kharagpur in the year of 2010 and 2014 respectively. His current research interests include deep learning, medical imaging, data compression. He is a TAAD alumni and was a visiting scholar at the Technical University of Munich during 2011 and 12. He is also a recipient of IEEE Computer Society Richard E. Merwin Student Scholarship in 2012, the Fraunhofer Applications Award at the Indo-German Grand Science Slam in 2012, and the GE Edition Challenge 2013, IEM UEM Distinguished Young Alumni Award 2016, MHLT Shanman Award 2020, IEM Distinguished Alumni Award 2022, the IEEE SPS Distinguished Volunteer Award 2023. He is a chartered engineer, senior member of IEEE, member of MICCAI, life member of IUPRAI and BMESI. He regularly offers the NPTEL MOOC on medical image analysis and deep learning for visual computing since 2017. So today we are truly fortunate to have him with us. We are eagerly looking forward to his insight on the transformative role of deep learning and medical imaging in healthcare. So please join us in extending a very warm welcome to Dr. Debdoot Sheet with round of applause. Thank you. What do you say?
Thank you. Okay, so good morning.
Good morning.
So my morning started long ago, but then like my morning started and then I was sleeping in the car. So that's something I have grown used to, and I still try to retain on to that habit, except for the 2-3 years of COVID has spoiled all of my habits. So till the time of before COVID started, so I can tell you, even February of 2020. So right before the lockdown was declared, the week before that also I was traveling on the weekend. So, and then I was doing some talks and some FDP somewhere. I remember, I think I was doing something in Bhubaneswar and I just came back, and Tuesday we had a national level project inaugurations meeting, and that ended at 6:30 and 7:30 there was lockdown. So it was something like that. Like a what we call an impulse function we just went through. Integration of that possibly like a negative step function just happened in our lives. So nonetheless, but all of those things and those 3 years were very beautiful 3 years, gave me a lot of time to introspect on whatever I was doing and what we were doing collectively at the lab. We did push ourselves to a very interesting on a vision board thing, but that part of the story I'm not going to tell today. There is a successive thing which happened as a result of learning from something which we did for in about a month's time, and made India quite prepared on reporting systems for COVID. But there are subsequent outcomes which came out, and in fact, the story I will tell around the diagnosis part of it is which is seeing the light of the day. So that's one part of it. The other thing is that I've been working on this particular topic for long. So I think oncology and machine learning, whatever you call as AI today, we used to call it signal processing back then, was something involved, including to the point that my supervisor believed that I should spend time in hospitals and in clinics as well. So I had my round of what you would call as residency. So along with what junior residents in MD do, so similar 8 hours, 10 hours. So there have been times when so the most grilling was the neurosurgery ward residency, because neurosurgery sometimes can go 12, 14 hours at a stretch, and then because the surgeon is not sitting, so you are also not sitting. We are not in the surgery room, but we are in the observation deck, which is, so those, I mean, the teaching operating rooms are basically like theatres. So if you are paid to not multiplexes but older like single screen theatre, then you have those gallery seats. So if you ever enter into those older medical colleges, then you will see that there are galleries as well, where all students stand and then they observe how a procedure is going on. And from the gallery it's completely glass, so you cannot speak, nobody below hears it, nothing comes over there, but you can just observe what people are doing. So I had those things as well, and it was very important part of my learning. So when somebody comes and says that we'll make this AI and that will help somebody do it, the first question which I ask is like, have you ever tried doing it yourself the human way? Before you come and say that AI is going to solve this problem for somebody else. If you haven't done, in fact I remember that there's a company called as AdNext. Have you heard about this one? It's a agri-tech company, IIT startup. Very senior people, you know, who had graduated long before me over there. But there was one point where there was some discussion they wanted to have on deep learning and computer vision put down to agriculture. So I don't come from an agrarian family, but then my immediate relations and cousins, everybody is into agriculture, and I've grown up between fields as such. So there would be periods when my parents would try to get rid of me as a young kid, and I used to also love it. So the whole summer vacation I would actually spend in the village. That used to be my whole thing. And then my grandfather also found that, okay, so he is one assistant you get, so let me take him to the field as well, and let him do all the things. So I mean, somewhat I had say 1 month of practical training every year on how not to grow paddy. Every time I attempted it, it would fail. But that made me learn. So technically I know 12 unique ways in which you should not be cultivating them. This is my experience, is what I find. So when I went to them, I asked them like, how many of you have ever even tried to maintain a garden by yourself? First thing, forget it, when you are a agri-tech company, everything understood. But have you even tried to maintain a garden by yourself? And have you been successful in having a plant alive for 5 years? This is a very big ask. Those of you who have a garden, a perfectly manicured garden, if you are doing it by yourself, you know keeping the whole thing alive, a single plant alive for 5 years is a mammoth task. Anything on a pot will be alive maximum for 3 years. After that it is going to go and die. Whatever be the robust species you are going to do. There is a lot of tricks it goes to take how to keep it alive. Simple answer? No. Thing I said is, first my simple thing would be, my humble submission on this is, go and spend a year in a farm and actually do a farming by yourself. You will come back, your ideas will be much more grounded. Today what you are telling, that a guy will pull out a phone and scan some sort of a brown patch on the leaf, and then we will send it to the cloud, do all of this. I said, I'm not getting into the tech stack. The guy will not carry a smartphone in his gamcha, on his shoulders, or even tied on his waist to over there, because the smartphone is a very precious thing. I mean, if that gets lost or damaged, he is going to sell one of his plots in order to get that one, and possibly he has only 4 plots. So most of it in the real sense does not even happen. So whatever you are asking for, that's what happens in corporate agriculture. It will happen in the grass fields of North America. If you look into commoditized sugarcane farming in South America, over there it will happen, because it's not individual farmers who are going to do that. But India is a very different setup. Here everything is small, everybody owns that. And when they say they own it, they actually mean that they own that piece of the land. Like they know it more than whatever your sensors can ever figure it how much is the organic content which is missing. You don't need to put down any sensors or anything. So that's one part of it in order to tell you. So the other side, why I was telling you that is that this whole thing of oncology, whatever I say today, will look very fancy. So, and I'm pretty sure you will walk out of this room with enough of a confidence going to tell that tomorrow I am going to launch a company on this one, in 5 years I will get an IPO because this product is going to be successful. And I will tell you that I have 15 years of experience. I have 17 years of experience working on this. Very few products. There is only, in this whole talk, I am going to show you only one single product with a company which is FDA approved and sells. Sales means it sells pretty much. I mean, today they have sold over 1 lakh units across the world. So, it's like just 100,000. It's less. It's not really large. We were aiming we would have made 1 million units in 5 years, but that hasn't happened. It's just 1/10 of that, what we were targeting. But it's growing. So, the truth is that it's not that AI can just bring and revolutionize things. It will never do that. What we need to be very cautious is, what is that repetitive problem which I was facing, which was useless, drilling, manual labor, or was time consuming. AI is just going to make that simpler and faster. It's going to offload those useless things from you. You just have to remember that. So, a simple example which I give is that in earlier days of email, when people had to write it on notepads or write it down on a terminal, every email you send at the bottom, you have to again type your signature. When you got down these web-based things coming out over there, the first biggest improvement was that there was an auto signature which was added. So at least like another 5 lines of typing got saved over there, that you don't have to do this. So AI is basically going to bring in these kind of small interventions over there. And more bigger, there's another part of the view which I will share a bit later on, which is that honestly computer science has not contributed to greatness of AI in any way. I know people over here will feel very sad, but let me say that material science has contributed to current dominance of AI far more than what you even think of. Mechanical sciences, specifically thermal engineering, has contributed even far beyond that. And another thanks you should always give to power grid. Without electricity, everybody will just stop over. End of it. Okay. So before I start, simple disclosure which my legal guys always want me to put down is that several people over the last years have funded me in several avatars, from startup to labs, from stock options to several things, and whatever I am going to tell is basically what I can tell, because in the last few years, last decade or so, that we have been funded heavily by these people to do all the crazy work which we do over here. So from there, coming to an understanding of, today people will relate that deep learning is all about it. And that's the biggest mistake anybody does. I mean, every 18-year-old walks in to a computer science program, or today even a data science and AI BTech program. Everybody is forced to open a data science and AI BTech program, thinking that deep learning is all about AI. And and they are sort of like the mighty giants of AI with their ability to do a pip installed PyTorch. Right? How many of you believe that? And everybody is a faculty member over there. You do, yes, correct. I mean, I get people who come in with that, and the first question I do is, so have you heard of LeanNet? Some of them will be bold enough, yes, very good. Draw the structure. Next thing is, calculate all the weights and biases, and calculate what is the total number of multiplications, additions, and bit shift operations happening over here. Gone. Done. End of story. So that used to be a persistent PhD level admission question. Every year I used to ask for the admission into the AI program. I said, you know AI? You say, do this. I will not ask you. Like, I ask them anything like, what is a topic you want me to ask a question from, which you have prepared? They're going to say, deep learning. I said, oh, very good. Let's do deep learning. I don't know what you came walking in, but I'm one of the guys who contributed. Like, our lab was contributing to writing 4 kernels inside PyTorch. So at that time, there used to be another language called as Lua, and there was a library called as Torch. I don't know how, does anybody know about this language called as Lua? It was like Cuba's response to American domination. So how many of you know that Cuba built a programming language? It was an interpreter-based language, but it had objects inside an interpreter. All of us know that compilers have objects. That's what we have always been taught. But then Lua was a language which was an interpreter. It was a just-in-time language, and it could handle objects. It could handle graphs, far beyond what people had thought of. So, and there was an excellent deep learning library which was written in that, which is called as Torch. And that is the precursor, and from where everything what you know today as PyTorch was actually born. There was in fact a linear algebra accelerator library inside Lua, which is called as Eigen. Have you heard of that? So Eigen is the linear algebra backend, which basically powers all of deep learning libraries today. Be it PyTorch, be it TensorFlow, be it MXNet, whatever net, anything which comes out, the accelerator for any linear algebra operation is only Eigen. And Eigen was originally written in Lua, which was written by a bunch of guys who were developing on old smuggled Pentium computers in Cuba. So this is where things were happening. So cut to short, where it was happening was something like this, and this is more of like to a non-computer sciencey background of audience, because I've been told that there is a mix of people over here. So how things evolved is in old days. Old days is 1930s, 20s to 40s we are looking at. So World War was a nice time. There was a lot of scientific developments happening. In fact, now that the world is in a state of war, you will see a lot of scientific developments happening. Why do you think that India sanctioned 1 lakh crore for R&D investments? Any idea? If we were not in a state of war, the parliament wouldn't have sanctioned 1 lakh crore. Pretty straightforward. Today, we are in a state of active war. And today's war is not fought with weapons. Today's war is fought on a different scale. It's an information war which we are fighting right now. So all of this got sanctioned because we are in the middle of that information war. Because these people who sit inside the parliament, who reflect the collective opinion of the remaining part of the country, has seen that in an active combat, the only things which saved us was all the deep tech in information space which we had developed. So the whole war with Pakistan, whatever went on, everybody has seen live telecast of it. And then this Air Chief Marshal was saying that there is this network of air safety which we have built up. You heard about this? Network-centric warfare and network control and everything. You know what he meant? Do you know what he meant? So, in Raisina Hills, they were sitting in a room which has a table which is made out of complete LCD. Okay, so 75-inch LCDs, 9 such panels integrated together. That is the table on which the map of that territory is projected with a satellite view. So it's an augmented reality system on which you basically have the real geological map with markers, everything, and a satellite-based view of in real time what is happening. So they could see our fighter jets going and bombing and everything over there. And then they could also have these like what is my radar signature mapping, what is the enemy radar, who is getting a lock, etc., sitting inside in that room. And how was that happening? So how many people were involved in all of this decision making and everything? As in this whole big war, how many people fought in that war? Any idea? We ended up fighting a war with a team of less than 100. It was an active war over 7 days, fought with a team of less than 100 people, but at the same time with roughly 100 teraflops of compute. 100 teraflops of compute, which consumes roughly 30 megawatts of power, is what this was. This is the real message behind the scenes. I know parts of it. actually intellect which was spent in that. So there were practically no lives lost. Machines let them burn away, nobody is worried about. And we are just like inches away from actually not even flying machines or anything. We can just do it from a pretty much remote control with electromagnetics. That's where we are looking. So every time this kind of a state of what happens, you would see that there is a lot of push towards actual science and innovation, because that's when people realize that there is a life beyond TikTok, and there is investments are worthy beyond codings of Prajwala gas to the rural masses mission as well. So, and the reason why I'm saying is that I ever try to look into the amount of money government spent on putting up codings for government schemes, you would realize at a point in time that it rivaled DST's budget allocation in the central fund. That's why I was saying that. So, in that backward days when the world was in a state of war, then there was something called as rule-based AI. And in fact, rule-based AI was something which enabled the Allied forces or the NATO guys actually win the war with radars. So what they had was a very simple thing. There were these beaming radars, and they would keep on sputtering noise over there. But then, which is actually associated with the enemy aircraft, and which is not? How do you do that? So they built up a set of rules. Like if you have this frequency in which you will see this speckle come up, if the spot size is so and so, in the neighborhood, if you see this kind of a tessellation, so they made a rule, and then you say that okay, there is an enemy aircraft which is coming. So that was all rule-based AI. Now, where is rule-based AI today? What did that happen? I mean, there it had just been war, but today, where is rule-based AI? Any idea? This is in this room. There are several things inside this room, in your hands, in your pockets, which make use of all of this rule-based AI. First and foremost is air conditioners. You set a temperature 25 degrees centigrade. It keeps on cooling. The moment the temperature drops below 23 degrees centigrade, it just shuts it off. The moment, then again it will heat up because there is no heat pump. It will go above 27. The moment it hits it again, shuts it on. So in control systems, people call that a switching mode control. You have that over here. I mean, this is simple rule-based AI. You have it in your phones. You have it in your watches. You have it in your laptops, you have it in this one, you have it in your TVs, like timeout. After 15 seconds of inactivity, just time it out. So it's monitoring several parameters over there, whether you are doing a key press, whether there is a network ping, etc. Is there a display going on? Am I present? So if I'm presenting a screen over here, it's not going to turn off abruptly because it knows that there is a presentation for you. So obviously there won't be keyboard activity. Something because somebody is speaking, showing that one. But then if I was not doing anything, I was in a normal desktop mode, it would have turned it off. I'm running on battery power in order to save that. So this is what rule-based AI was. Then people realized that you cannot solve everything with rule-based AI. So you needed to have certain thing called as a learning of decisions over there. And then came down this next one, which was classical machine learning. You had Bayes rule, you had random forest, you had support vector machines, etc., etc., and then came in neural networks. And people thought that we have a huge powerful thing, now we can make an electrical circuit equivalent of the human brain. In fact, like, the first set of neural network papers were published in neuroscience journals, they were not even published in electrical journals. I mean, neural networks were not even considered mainstream computer science till a point of view. Today, whatever everybody is jumping around in deep learning, that this is what computer science is, and the whole computer science community never even considered as science, forget computer. So we just throw it away. Well, like an outcast, completely outcast. So all of these which came in, that was with learned decision models, and that was classical ML which was happening over there. And in fact, you have a lot of these classical ML at your houses today. Example, so you have washing machines which calculate a lot of factors. What is the temperature of incoming water? What is the kind of this knob I have tilted to give what kind of a fabric? Then what is my flow line velocity? And what is the kind of a fabric softener and detergent I have given? And then it will calculate, and you will see it will give you some time. Like it will take 2 hours, 1 minute. But that is an estimated time. You would say that when you start the machine, it will never end in 2 hours, 1 minute. it can sometimes end in 1.5 hours. Sometimes it will take it longer than that because there are sensors which are monitoring the outflowing water and the quality. So whether it is below a certain particle matter levels or not, whether all the soap has been washed out and it's clean water which is flowing out or not, based on that it will auto adjust. So it's basically learning. Over a period of time it is adjusting itself. So you will see sometime about roughly a decade ago, there was a lot of these washing machines, then refrigerators, then microwaves which came out with something fuzzy logic based. And then like there would be one machine with fuzzy logic and then people will just run in like that is 50,000 rupees more than the other machine. And then everybody buys it. Like this is magical, this will transform my life over there. That was just one additional controller over there which could, like your earlier machines were just like what I would say, simple timer and a timeout operator. Nothing, it was just an interior counter and that was in the microcontroller. In the next one what came down is you had multiple such counters, you had some more parameters over there, some additional multipliers happening. It was still the same silicon on which things were happening. Possibly like you had 2-point arithmetic instead of fixed point arithmetics being put over there. That's the only thing. So there was no technological revolution. The marketing guys found out a nice term which nobody understood and people just rushed in. So today you would see laptops getting sold and phones getting sold as AI co-pilot phones and AI ready selfies and I mean even like the guy who came to sell me a laptop, he was telling me this has AI. I said, so what do? I am the AI. You know, what will that give to me? I had to go and ask him like, does it have a programmable NPU? He looks at me. I said, forget all of that. Do you have a brochure? I want to see what is the processor's make and model number. Rest I can find it out. I don't need you. Thank you a lot. And then eventually found out like, okay, it had NPU. I would love to get a device with an NPU which is consumer grade programmable so that I can at least program things on the NPU. Nothing other than that. Now, then I got a bit curious. So, about in 2018 or so, we were contacted by a bunch of companies in the Silicon Valley. It was like when they were trying to create a lot of, say, small scale, I would say picowatt level neural blocks. Okay, so to make it simpler, it's like for most of deep learning, everybody uses GPUs. So when you have a code already written down, what you are going to do is just an inference. So in order to run an inference, you don't need so many like kilowatt consuming GPUs over there. You can actually bring down low power hardware. The moment you can get down the low power hardware, what it means is that you can put it on your phones and still the phone battery will last for like 8-12 hours. It will not just get exhausted. And so mainstream companies like Broadcom, Qualcomm, Realtek, MediaTek, who do processors for phones, they were not yet focused on getting these kind of GPU-like or massive multiplier blocks. So essentially these are massive multiply and accumulate units, a specific piece of hardware. So people who come from processor architecture understanding, then you remember that before the Pentium series of processors, when 8086 architecture was there used to be something called as an 8088 math coprocessor. A simple chip which will be put down over there, and then PCs used to be sold at that point of time that this support calculations and math at blazing fast speed and everything. Because like in order to multiply two numbers, you don't have to iteratively keep on adding numbers, which was the 8086 way of doing it. So what these are basically like eventually later on you got down something which is called as a multiply and accumulate block over there. So you could have two arrays, do bit by like element by element multiplication and then add, essentially a dot product operation, which is what fuels most of it because you will have convolution like operations. So these NPUs are basically a massive array of such kind of multiply and accumulate blocks. So you can have a row or a column getting processed in one shot. This is what they were. So they were doing, and then these guys had contacted us, and we figured out, okay, whatever you are doing is old wine in new bottle, because we used to call so people who come from signal processing background and say VLSI signal processing, you know about something which is called as a systolic array of processors. What about this thing? Quadic? Anybody thought about this algorithm? Okay, so that's the unfortunate truth. So, like things what drive today's AI have been there in signal processing for since 1970s, and in a massive way. And then it's just that we got down them on a commodity scale hardware because the knowledge was already existing. So when I look back into what is this NPU, neural processing unit, essentially it was very simple. It was just a systolic array of processors and nothing other than that. A small set of arithmetic units, arithmetic and logic units, but massive amount of them, everything working on fixed point processors. Because you have massive number of parallels, so you can do a lot of parallel operations over there. We'll bypassing the whole CPU over there and keep it reserved for some purposes. That's the only thing which changed out. But if you honestly look into it, then who was powering it up? Not ability to write codes. It was ability to execute crazily written code. So a computer science guy, a computer scientist is always going to assume that okay, provided I have so and so much order of parallelism available to me, I will be able to get things done in such and such order of complexity. But that's a hypothetical thing. Provided I have the ability on hardware to do. Who was building the hardware? There was some electrical engineer who was building it because there was a material science guy who found out that materials can actually sustain that kind of an operation. And there was a thermal engineering guy who figured out that yes, I can also dissipate the heat over there. And there was some metallurgist who also find out that okay, we can have say room temperature gold wire lines over there to conduct these electricity without having any kind of a corrosion and which can last a point in time. And then there were some polymers and plastic guy who found out that I can put down a good amount of packaging on top of it so that I can make it weather resistant. And then like, all of these set of people who were doing it. And why am I telling this for computer science? Because you need to understand that our ability to deliver AI has not been just a contribution of people from a field of computer science. It has been a contribution from a much larger field, and it's its whole field of sciences and engineering which have come together. Now, and that those things have come up, that we can do massive order of computations, really led to the growth of this particular field called as representation learning. And representation learning, whatever we see over here, was another interesting fact. So you could do this thing which is called as learning of features. And there is another last ask people who come from say some sort of a math allied background is, can you give me a simple example of one algorithm which can learn the most appropriate representation of features from the data? You don't need to have an analytical equation written down for how it can get a data point casted onto a lower dimensional feature space, but it can discover that analytical representation by itself. A very simple example.
So distance vector? Distance vector?
Something related to vector, nothing of a distance vector, you are close to that.
Line equation?
Yes. What is that algorithm for? Part of eigenvectors? Singular value decomposition. That's the most fundamental representation learning which ever existed. Provided you have everything on a linearly expressible point, then you can have these kind of singular value decompositions, and eventually it was found out that you can do something like called as a kernel tricking on singular value decomposition, so that you can always break down any kind of a nonlinear thing to a set of piecewise linear options and then solve it. So this representation learning also exists today in a consumer grade device. Any idea? There. You use it. Every one of us uses it rampantly. It contributes to the world's largest single consumer of internet data traffic.
Google search?
No. Multimedia. Simple multimedia. We watch reels, shorts, YouTube videos, podcasts, videos, matches online, web streaming essentially. We also upload videos. But there is a skew. So the amount of downloads is 10 to the power of 3 times more than the amount of upload which happens on the internet. Over there, you would have a compressed bit stream coming to you. Most likely use of most likely format of this compressed bit stream is HEVC, high efficiency video coding format. For your images, it is HEIF. So today on most of your Android phones, Apple phones, anywhere, you get down a format over there which is called as HEIF. So there is an option inside your camera app which says that store high efficiency format images, and everybody turns that on. I think from last year it was a default which started coming in. So you have to turn it off so that you get down the classical JPEG. HEIF has the basis vector for projections, which was actually learned from the data. Why it is more efficient is because based on an image it can find what is the representation it needs to store. That's the beauty which is going on. So all of this, and you know what is the fun of it? This representation learning and HEIF, this is 2010. It was invented just 15 years ago. The whole scale at which things are translating is coming shorter and shorter. It says, and we are in a very interesting point in time. And then comes down this whole thing around deep learning. And the most popular use everybody does is Ghibli art on ChatGPT. You're welcome. So Ghibli art on ChatGPT uses transformers. ChatGPT is just a generalized transformer model, and then you also have the Ghibli art, which is just a convolutional transformer and nothing other than that. And what are those transformers? Simple neural networks. End of the day, if you end up the whole setup writing that bunch of equations over there, ever try to write the backprop equation for a convolutional model? You will see a fun. After some time, you will realize that it is just a bunch of matrix multiplications. Stupid matrix multiplications. So I was doing that in class one day, and I have this whole thing that the smallest of the models you ever teach in for deep learning is linear 5. So I gave this exercise. I told the students that let's do something today that I told you how to do it block by block. So today let's use the board. I will write from left to right the whole forward equation, and then we will also write the backward equation, the whole backprop. We'll derive all the gradients and everything. We write it in matrix forms so that there is not much of an issue. But then we'll calculate the consistency all through. That all both of us are right. We did that. One guy, generally like very fidgety kind of a guy. I know that this guy is smart, but his attention span is also very low. That one day I found this guy, he gets so interested, he doesn't even lift his head to look at anything else. He's just solving it by himself. And then he walks up to me and says, this is just another bunch of matrix multiplications. I said, yes, you're right. At least like once in my life, in my career till date, that I've been teaching deep learning for 15 years now, that there is one guy who realized that it's just another bunch of matrix multiplications over there and nothing other than that. And imagine this, people walk into the class, these are 4th year students on a 5-year 12-degree program in electrical engineering and signal processing and machine learning, and they walk into this class on machine learning for signal processing, assuming that there will be something great. In fact, the way like decision trees are what we used to solve by hand. You don't need to write a code. I will teach you methods by which you can really accelerate by hand solve. Then they walk out of the class and say, if I ever knew that deep learning any time earlier than this, that deep learning was just another bunch of matrix multiplications, I would have been more serious to do the linear algebra class and not actually wasting my linear algebra class timings in order to write PyTorch codes. Because I know that will never mean anything. I can just solve it with linear algebra. And these are a bunch of guys who have, so yesterday I got an email from one guy who says that I coded down the whole library by myself. The whole PyTorch base functionalities, he ended up coding every single thing by himself without using Icon as a backend. So essentially he made his own deep learning compiler over here without needing anything, base written on Python. And now he says that I want to write this in some other language, you tell me on what to do. So it's another bigger question he gave it to me. I have to figure out what to tell him. So this has even become commoditized. Imagine generalized pre-trained transformers, GPT, the transformer model. When did it come out? It was 2021. And you already got a commoditized thing in 2024. People using it so massively that today OpenAI is building up 1 gigawatt data center in south of Texas, the Stargate project, in order to fuel up the world's 10% of the requirement for using GPUs. It has gone so high. It has gone so high that our own cloud providers over here in India, Kruthrim, is saying that they want to commit to building a 1 gigawatt data center in India for India's homegrown LLM models, which will use all of these GPT-like things, because we will be using. So in fact, like, it's not very far off. The Indian language stack is getting pretty high. So you would, and how you would have access to that is not even on smartphones. That's the fun part of it. We are looking at where there will be a dial-up number. So all of this again, I go back to the farmer model. So the farmer has to ask a question. What he's going to do is he will dial up a number. He will speak on phone. On the other side, there is no call center representative who is going to respond to them. There is going to be a GPT model which is going to respond to them in their own language, in their own intonation. So whatever is the linguistic general parlance in the district from where he is calling, is going to get down a response in that language. That tone, it's not going to be one common thing. It's not going to be that railway station announcement like ladies' voice where in between there are different tones which just pop in. That will not happen anymore. That's the preparedness where we are. Other side is like, now people who do call center jobs can also figure out what is going to be their relevance. So when people say like people are going to lose jobs, yes, people are going to lose jobs because like irrelevant jobs will just be done away with. Anything which can be automated will be automated. And there are several things which can never be automated. So the guy who writes the GPT model will still not be automated. Yes, obviously, like your ability to write an HTML code in order to develop a course page is going to be automated. In fact, like yesterday, one of my colleagues from power electronics, very far away from anything to do with computer science, that guy comes and says that I built up this web page for my course. And I'm like, yeah, wonderful, you made a great development. Then he says, and I did not write a single line of HTML code. I asked ChatGPT to do it. Very simple. He uploaded the PDF of the course content and gave his contact details and everything. I just put on a clever prompt over there, gave him and then said like, give me a bare one HTML5 and a 3 device compliant CSS supporting this one. So that is what I told him. That write this one additionally, then it will open up very good on your mobile or your tab or even on laptop. He did all of this, it came out. Yes, web developer, one. Nobody is going to do. I know a 60-year-old guy with whom I work on some deep tech thing, I will come a bit later on. He made our website by using Microsoft AI Copilot. He did not even go to like, I will not write a single line of HTML code. I was telling him like, okay, insert this one, this is the script you can insert over there. He said, like, I don't even know where to insert because I did not write it. Copilot wrote it down for me. So I was worried at a bit of time, so in fact like I did a complete code review of the whole HTML which he gave me to see if there are some spurious things on it. So that's where things are moving. So why was I giving you these anecdotes? There's a reason. The whole thing is, what I'm going to speak now is about these kind of small interventions which we have been putting down into medical practice in order to automate shorter stages which used to be very laborious for a doctor, and how that is helping them transform. So first and foremost, some basic run-of-the-mill concepts which I want to make it clear. In this whole world of deep learning, there exist two different paradigms on which people work. One is a genetic paradigm. A genetic paradigm is basically denoted by something which is called as a joint probability occurrences and whatever you say. So it essentially means that what is the probability of two events to occur together. So when somebody says that you're using genetic models in order to answer to certain questions, etc., then what you are basically saying is, that's what we as human beings at some point of time also do, is like, if I'm posed with a bunch of questions, then what do? I try to find out what is the likely association with the event in the question and the possible outcome. And whichever is the most likely one, I would answer first. Okay, so simple example, I'll take a medical example on this one. So somebody says that I get periodic fevers every 12 hours, and when I have when the temperature rises, I am also shivering. Okay. And when is it happening? It's happening around this time, July, when it's monsoon. What's the most likely diagnosis is that you are malaria. Next is like somebody says I am short of breath, my nails are turning red and it's bleeding, or somewhere like I can see my eyes are capillaries in my eyes are also red. Then the likely symptom is that you have dengue. And then you will put all the other vectors in relation, like is there somebody who has a dengue in the neighborhood, is there this pandemic reported or not, all of these things. This is from the first principle. And any idea when this first principle was discovered of generative models? Historical date here. 1998. This is Bayes' theorem. When was Bayes' theorem discovered?
I think 60s or 70s.
1600. So generative models are from 1600. So essentially it's like 400 plus years old, whatever we are looking at today. In everything I will break it down into that probability. Then like at some point in time, there was something with the neural network I was solving and then it boiled it down to quadratic. I think I have it over here. And then I asked people like, when was the solution for this first found? Roots of a quadratic equation. When was it first discovered? Sridhar Acharya's method. When was that? 800 BC. So certain solutions for deep learning actually were discovered in 800 BC. Not even today. So somebody says this is high tech of the current tech. No man, this is like too old. This is too old. What is current tech is that your ability to implement it on a consumer grade. And that was happening because of people which, like there was a lab, I think 2-3 doors earlier, solid state lab. So people who do things over there are the ones who actually got it. Like, they were the ones who were doing cutting edge. The other guys were not doing cutting edge. We were still just dragging onto their edge over time. So first, this is generative. Now the other side of the problem which we look into is discriminative, which is given one event has occurred, what is the probability that another decision can be taken? These are two sides of it. In medical sciences, the later is of paramount importance. The later is of paramount importance. So, given an event has occurred, what is the probability that a decision can be taken? So it's conditional, it's not joint. So what is of paramount importance in medical science is that. Having said that, that is a decision-making problem in diagnosis. But generative has a lot of role to play in detection. And that's how my talk today is going to be. I'll start with the generative model. I'll show you an example, which is a product skill, by the way. And that's what is selling out in the market. I can very proudly go and say, okay, we have sold it. I did not make money. I made all the money when we built it. After that, we did not make any more money. And then the company is making money, but there is one technology which is out over there. At least like when my son becomes old enough, then I can go one day and get his blood test done and then say, see, you got the blood test done in 2 minutes because your dad built up something. I mean, they are sort of like proud moments you go and do. So once my mother was getting misdiagnosed with uterine cancer, so she was almost being forced at that point that you have to take this surgery. And then she always like, what do you say? I mean, the only son. And then she knows that okay, this guy did a lot of like most of the discussions at home when I was doing my PhD used to be around like general awareness of oncology at home. To a point that I stopped doing that because I realized that my parents started finding every single thing as like they are having cancer. And I stopped doing all that. Like, you are overdoing things. Yes, we do recognize patterns, but then sometimes you are like overdoing. That is not even a symptom. Nothing is happening. You have to go and tell them like, see if it is consistent for at least 3 days. Then you will tell me. Then I will see what to do. You don't come to a conclusion. So like, sometimes you will see that there are lumps under your skin. It happens, they are immunological responses. And they will vanish in 6 hours. Like every time there is a lump, I am getting a cancer. You are not getting a cancer, you are not that fortunate. You never get it. So, I'll go through that. Now, before we get into that, this is again for a very generalized audience, keeping it low math to the best possible extent and with maximum figures. So, if you look into machine learning, then you can split the whole task of machine learning into three broad groups of activity which you do. And the reason I wanted to start with this one is that because I know a lot of you teach machine learning or are willing to teach it at some point in time to your students. So please take the pedagogy in this kind of a way whereby you can abstract out different parts of it and then explain them each part in a much better way. Otherwise people generally have a confusion between what was that led to the change, whether your power of data was contributing or your power of modeling or your power of learning and optimization was contributing. Nobody understands that very clearly. So the three things which basically has led to whatever happens in machine learning. First is the data, what we call as the data space of understanding this one. Now, what you see over here is the least complex. So this one is the least complex thing to solve, which is like you have lot of data, there is enough of variance, and there is no biasness towards any one particular category. That's the ideal situation, which is like, can I sample the universe? Theoretically, like if you're doing discrete maths, theoretical statistics, everybody will say quantum physics, yes, that is possible. You ask a real engineer and you go and get down the data, actually go and sample properly, like your sampling theorem, that one guy, Shannon, whatever he did, like he wrote down great bounds, but ever try to apply it in real world, then you will get into all the problem. In electrical engineering, we have this very famous thing. We basically do it as a ragging exercise on the students. The teachers can do it, but then grand Wi-Fi is now banned. So we used to tell them like this, that Wi-Fi signal is 2.4 gigahertz. So it is a sine wave. Now if you want to sample Wi-Fi signal following the Nyquist rate, what should be your sampling frequency? Like I will come and say it should be, if that is 2.4, so it should be 4.8 gigasamples per second. Now I said, okay, if you have a 4.8 gigasamples per second, how many bits of ADC you will use? And now somebody says 16 bits ADC. I said, very good. Now what type of an ADC will you use? Then somebody says flash ADC. I said, no, that is very costly. Your router, that Wi-Fi router which you buy comes for 800 rupees or something. If you put a flash ADC itself is 80,000 rupees. How can you put it inside that? Then some other like geek guy over there will come and say, no, we will put down SAR ADC, successive approximation register. That is going to be a best of both worlds because you have a single bit comparator over there which is going to solve. Very good. So now you have what, 10 bit? I said, yes sir, 10 bit. 10 bit is enough. Very good, 10 bit. How many clock cycles will it take to convert a number? Maximum. So if it is a 10 bit ADC, then it will take 11 clock cycles, all from theory. Very good. So now I have my samples coming at 4.8 gigasamples per second. Every sample has to be encoded in 10 bits, and you are going to take 11 cycles to complete everything. So what should be the clock frequency of the crystal which is going to power it up? Then you multiply 5.4 gigahertz, 4.8 gigahertz into 11. Okay. So yes, like that is going to be something in the order of 52 gigasamples per second. Right? So where is the 52 gigahertz crystal? And the next thing is like, what was the frequency of the microwave transmitter? Suddenly he realizes microwave transmission happens from 1 gigahertz onwards. So we have put down a like 52 gigahertz crystal. Basically I am doing microwave. Now microwave cannot happen from crystals, is something he has studied in textbook. They said, so what can you do for that oscillator? No, then we can bring in a cyclotron to do that. I said, okay, cyclotron is too big, clastron will that work? Yes, clastron will work. Sir. So what is the price of a clastron? So like, you basically trap them inside all of this. Then where does the whole solution come from? The whole solution comes down from a much rudimentary thing which is known as sampling of band limited signals and then what we call as mode and transfer. So you never sample at that high frequencies. What you do is that whenever you sample, you will have a thing called as a folding effect on the spectrum. And the folding effect on the spectrum will get you a part of the spectrum at a lower frequency part. So you can basically extract everything associated. So your bandwidth of over this 2.4 gigahertz central frequency is going to be something like maximum 400 megahertz. So what you need to do is you just need an 800 megahertz sampler in order to sample. That's the simple solution for this one. The theory goes much deeper in digital signal processing, but this is how people miss out on the concept. So why I was telling this is that in theory you can do a lot of things, but in practical You know that you will never, because if you have to make an 800 rupee router, all of that theory is never going to work. So now comes the practical theory. Let's break it down. Can I do an undersampled sensing? Yes, I can. That was another part of the theory which Shannon had proposed out. Nyquist could not with his limited understanding. And then we use that in order to do that. That is what powers our things. So essentially what this guy Shannon had done was this kind of a scenario. I will get lesser number of samples, but whatever I get is representative enough, provided I have a model which can represent that appropriately. Bringing that to the machine learning part of it, the next thing is I have a model good enough to represent it with less number of samples to do that. So this is important. Now the model, the simplest of the model is at any point of time is going to be a linear model. Y equal to mx plus c. M and c, two variables. Solving for two variables is always easier. I mean, what do you need? You basically need 3 points, and not even 3 points, just 2 points. You'll have 2 equations, 2 unknowns, solved out. If you have 3 points, you will have an approximate solution. Something, but whatever happens, you just have 2 variables. That order of complexity is always dependent on the number of variables. But the issue is that you can fit only statements. Everything in real life cannot be just fit with statements. If you have, say, a sinusoid or a curve or something, then you can come back and say, I can do pieceways. That brings you to the point, how do you split into pieces? And that is what we call as the control plane of the problem. Everybody is generally worried about this one subject called as control systems. Anybody who is not worried about the subject called as control system, even in faculty? Yes, no? Hey, how many, is there somebody who teaches control systems? So, are you confident about control systems? So, how many times have you ever tried to implement a control system on the gas cylinder of your kitchen? You'll run out, guarantee. I basically, so my department has more number of control system faculty compared to everybody else. And out of this all control system faculty, nobody does industrial control systems other than one single professor. But this one professor who does this control systems, he does weird control systems, I will tell you. He was part of the team which was building up the control system for Agni missile. I mean, like he will do engineering. He said like, I will not do trivial engineering. I will do like this. Like when we launched PSLV rockets, so I will do control of the PSLV rocket. I will do control of the Agni missile. He worked out even with the guys who were building up the control and navigation for the BrahMos missile. And the crazy part, he spent out 6 months in a Russian Defense Technology University in order to learn Russian technical writing so that you could figure out how those guys were building it over there. Because it was a joint technology transfer. So this is one crazy guy I have. So then you go and ask him, how about writing people? Say, very boring. This math is very boring. Okay? The actual fun is that your missile is actually going straight and hitting the target.
So even if you teach computer networks, there is physical layer. Channel capacity. But if you teach in this method, why you need a channel capacity? Next student will never come to, at least in private colleges, never come to your class.
My take is that that's a misconception we as teachers have. What I have found is you expose them to the most tough problem. Initially they will be reluctant. After a few days when they see that there is no way of going out of it, they will really start reading. Once they start reading, they will actually get into it. And this is my, because I will tell you, I run a lab for all of these deep learning. You need a lot of compute. We have a full micro data center in the lab. It's a 40 kilowatt consuming thing. 1 teraflop is the combined compute capacity built across generations of CPUs and GPUs. Some 20 odd servers connected together. I don't have a technical staff to manage and maintain it. We don't have annual maintenance contracts. There's nobody to even clean it. All the PhDs in the lab have just learned how to upkeep that one. I told this is there. I can fit on more machines. I can do it as a prestige issue. This is a cut. Yesterday when I walked into my lab, I see one of these guys actually dismantling a Skylake series server processor, which is a very specialist way of doing it. Basically, you need a separate kind of a screwdriver to dismantle it. There is an order in which you will have to dismantle, and the pin grid array over there will just crack out. Because it has a 256 by 256 ball grid array underneath. That is the number of connectors present on that chip. So if one slight mistake, it just cracks out over there. And I was amazed. Even I don't have the courage, nor I have the know-how to do that. For that, I would have anyways called a specialist to do that. There he comes in by the tool, and now I found out this guy and said, like, but where did you get the tool? He said, see, they use something where there are 4 screwdriver heads. If it fits onto it, and mechanically it removes it out. So we found out that there is the pressure sensitivity. There is some 21 psi or something is the limit. More than that, it should never go when you are mounting or dismounting. They bought 4 pressure sensitive screwdrivers, which measures that pressure. Now 4 pressure sensitive screwdrivers came down for something like some 10,000 rupees. That whole device which does that comes down for 2.5 lakhs. He got it, think for 10,000 rupees. He knows that anyways I sent it off in contingency bills. 4 research scholars standing on 4 corners, each of them on count, and there is one guy who is the orchestrator, like orchestrator in a band. 1, 2, 3, one move. All of them do a move together. Sing. Everybody is what? So somebody says, hey, mine is lower. Then like others also make it lower over there. So this is how they orchestrated. They actually pulled up this one. And if I would have lost that chip, I would have been fired by anyway, because one chip is 48 lakhs. A single chip. Imagine the scenario. So push them to do it. They will. Why am I coming and saying this? Because this is my experience. I want you guys to push it. Because otherwise it piles on a next level of a problem. See, at IITs, we basically take in students who have graduated from institutions like yours, like to the first level of the training, that is undergrad level. We take them for graduate studies. That's where our prime interest is all about. I mean, we do undergraduate programs are there, but if you look at the count, then the number of undergraduate students to the number of graduate students, which is masters and PhD, there's a different skew. So most of the population is just masters and PhD, unlike what people generally want to think. So I need better quality people who are open to taking up these challenges over there. So expose them. Yeah.
So out of box, since you are showing a data space plane, right?
Yeah.
2 coordinates X and Y.
Oh no, there is nothing about which X and Y, that X1 and X2.
Yeah.
Oh, just a 2-dimensional representation. Hypothetical 2-dimensional representation.
I thought something.
You can make it X1, X2, X3, 3-dimensional. How do I visualize on a 2D screen? That's why I just kept it. And then you have this control plane, where very old days, simplest method was Bayesian. So maximum likelihood estimation used to be the best way of fitting down any data to any model. And today, then there was this mean square error, which was essentially regression modeling and fitting onto those kind of problems. And then you come to what today we call as perception learning or perceptual loss, which is what we do through adversarial neural networks in order to train generative models over. Now, going to that, there are ways you can address this problem. So, taking on to that example of sensing undersampled signals, and a simple thing in case of over here is like whatever you have as your data points which are sampled, there is something which is called as augmentation. What about this data augmentation? Everybody has heard about it. But then there are interesting characteristics. You need to know, you need to have a very deep understanding of what are the set of valid augmentations, what are the set of invalid augmentations. Otherwise, like, you're going to make a mess of it. So if I'm looking at some microscopy image, this is a white blood cell, so I can rotate them, it will still have the same pathology, there is no problem. I can flip them up, down, I can reverse it, whatsoever. But then, if I take a cow, and in order to augment the data of a cow, I flip the cow upside down. How many times in a real world scenario will you ever see upside down? So anybody who trains a model without knowing this one, that in real world this is an invalid operation, is going to end up basically training wrong models. So that's why this data augmentation is called as an art rather than a science. So language specialists or data specialists. You know where data specialists for like people are hired from. So if today most of the industry is basically going towards natural language processing and conversational AI. So these are linguists, people who study language sciences. They get hired by TCS. There is a higher probability of somebody who has studied Bengali or Sanskrit to be hired by TCS than is the probability of somebody who has studied a BTech computer science and is a 9.9 point. That's the reality. Because you need more people to solve this art. The science part anyway is that like for one guy writing a neural network, you typically need 100 people preparing the data. So that's how you will find people who have done BCom getting a job in TCS, but then your own kids who have done their BTech in computer science with a 9.9 CGPA not even getting a job in TCS. You have seen that. Students agony, teachers agony, parents agony is even more. The reality is that nobody needs people to write HTML codes. They need people to do something else, another level higher. So a BCom guy was getting thing over there because they were generating to the data curation. BStat, BMath, BSc Maths guy was also needed over there because you needed somebody to do the fundamental math. Somebody needed to write down the discrete structure before the data structure could be designed, before the database could be designed, before a coder is going to code down the database. So that's why it was more important to do maths. You would see newer universities starting these BSc programs in mathematics with specialization in data engineering or data sciences. They cannot call engineering, they have to call it data sciences. So they are important, they are relevant because these guys do more fundamentals over there. So coming from there, the next part is to look into the model space of it. Now, linear models are always easier to solve, but then data is not always going to follow. So say I give you this kind of a problem where the discrimination boundary is like curve, a closed curve, an elliptical curve over here. Now, you would need obviously a quadratic model in order to solve it, but let's look into the degree of freedom of a quadratic model. So how is it modeled? Ax square plus by square plus cxy plus bx plus ey plus f. So how many is equal to 0? How many free variables? There are 6 free variables. Compare that to a linear model, only 2 free variables. Now can I convert such kind of a polynomial model to a linear model? Answer is yes. I just need to have another layer which can do something which is called as a kernel trick. I can do a kernel tricking on that so that it converts to this. Now what is that kernel tricking over here? What can be the transformation which I apply to the left hand side of the distribution to get right hand side of the distribution? It's a very simple term. Something called as a polar to Cartesian conversion. So find out the centroid, project every single data point onto an articular representation. The right hand side is basically x1 axis, horizontal axis is the radius, and the vertical axis is the theta.
Hoffman transformation.
So that's polar to Cartesian conversion. That's what you did over here. So half transform. So how old is half transform?
Same. I mean, that is
1910, 13, something is half transform. That's what you have. Everything was there. It's just you need people to rightfully put it into place. That's the fun. Then comes this control point. Now, in today's world, when we look into these kind of generative models, we have a very simple example, which is like, I want to do a sketch to photo CNN. What is the purpose? I have a CNN, I will put a sketch inside it, say my dream house. Not my dream flat, my dream house in my plot. And then let the CNN render it out. Okay. So the CNN renders out something like this. Does it look like a photograph? No. So what you will see is that the mean square error between pixel to pixel, that is going to be low. But if I ask you this question, does it have a perception of a photograph? No. I want it to look like a photograph. pixel to pixel errors. That's very high because they are not matching. The colors exactly at those locations are not matching with those colors. But perceptually, we as human beings, we would say, no, that is more of like what my house is going to look like. So how do I encapsulate that, what was in my mind? And that's where all of these things called as discriminators actually started coming into play. So this was kind of a spot the difference puzzle. So in newspapers, you get these spot the difference puzzles. You have two pictures side by side and spot 5 differences over them. So you train a neural network to do that. And now what you do is, while you are training a neural network, you give that feedback to this sketch2 photo CNN and say that, see, that guy is able to discriminate. So you should update yourself so that he is not able to discriminate between them, which is like I want to fool that discriminator over them. And that's from where all of this name comes in. There is a term called as adversarial attack. Within adversarial network, you have something called as a generative adversarial network. So the generator, which is that sketch2 photo CNN, was attacking the discriminator over here. That's from, and it was adversarially attacking because what is the state of the discriminator? That guy knows it cunningly. Somehow he has a mole. There is a message passing which happens from here, but the discriminator doesn't know that the generator knows what is its status. So it's a one-way traffic. So you now keep on attacking that and you can monitor it. So later on I will come into the actual implementation of how we end up doing that. So I believe this is a good time to take a break. Yeah, and then we will get into 3 scenarios one by one with another thing of the content as well. Okay.
পেপার সামারি এবার যদি লাগে লেখা নেবে আপনি করে দিতে একটা লাইনই খোঁজা দিচ্ছি হাফ ঘন্টা বললো মানে হাত থেকে ইয়ে করে মানে বেকার সোজা করে বিদ্যাস মানে নেই হবে ঘুরি ঘুরি সোজা করছে না বেকার সোজা করছে স্যার দিয়ে রেখে এটা দিয়ে রেখে দিদি এখানে আসুন একটু এই চলছে দিস ইজ হাউ টু টিচ আপনার আইএম কোন ব্যাচ
Just Okay, so coming back to the use cases, so where we are going to look into. So the first part of all of this as was given was detection. Okay, so there is detection, diagnosis, and then there is therapy planning over there. There are three different scenarios of at different stages that whatever work we have done. So the first part of detection is where I'm going to give you the scenario around with deep super resolution for digital pathology. Now, in simple terms, if you look into traditional pathology, so how many of you had the misfortune of ever getting a pathological test done? All of you. Everybody had at least a blood test done at some point in time because everybody.
Just one information for you, we have a practical session, so at the day end. So we have taken all the attendees to the lab and we have shown some of the basics.
Oh, everybody knows, has visited path lab.
Hopefully.
Oh, great. So you know what is a slide, what is staining, and what is microscope, and what is drying, what is a microscope. Good.
First
So
day lab it is shown.
yeah, I just have pictures and I will make it simpler. I will just have one point where I will show something which is called as a spectral characteristic response. Interesting engineering term, which basically means that why does a certain tissue look red under a microscope? Okay, so if you look into this, even today, most of our health system just relies on this. Just go to the nearest government hospital, sub-divisional hospital, you will still see this kind of a setup, and this is there from what 1700s. This is when we have been doing this. What does that look into? Is it something like this? I will have an organ where I want to do something, and then I want to investigate it by cut out a mass of tissue, do a certain set of processing, and then put it inside a wax block. Okay, I'm just simplifying the process. And then you put it in a machine which is called as a microscope, which cuts it into thin sections of 5 micron, 3 micron, whatsoever. And then you mount it on a glass slide. And then you put it under all the rangoli staining things, and the tissue plays holy. And then out comes from that another full tissue. And then you put it under a very costly thing which is called as a microscope, which you can buy on Amazon for 10,000 rupees as well. You can even buy for 1,500 rupees as well. There is a pocket. I should have brought certain licenses. No, like you get 40x magnification on this small set cassette-sized microscopes, which come for nearly 7,000, 8,000 rupees or not much. We use it to clip it onto a phone and acquire images. In fact, this one I will show you an example of where we are going down deeply on towards that as well. And then you see an image which is like this. So in simple terms, in more of engineering terms, what happens is that I give a wide band spectral signal. So imagine it to be, so you have this interesting thing that if there is an impulse function, what is the Fourier transform of an impulse function? It's a wide function, all ones across complete frequency spectrum. So that is the same as something like the sunlight. So what all parts of the optical of wavelengths of photons, it's completely spread, but it may not be uniform, but it's a wide band. Now it passes through this part of the stained tissue, and then for different pixels or different locations, some part you will have more transparency to red, some part you will have more transparency to blue, and based on what is the nature of the tissue present over there, and dependent on the protein in the tissue, you have a certain binding of a chromophore over there, and associated with that is the color which comes out over there. So if it is red, then in this case it was essentially a cardiac plaque we are looking at, so it was fibrotic tissue. If it is blue, then it's a calcified mass. Now, if you look into this whole microscope, then this is an interesting piece of electro-mechano-photonic instrumentation which is present over there. Every single thing, and also thermal, metallurgy, material sciences, everything. Everybody has a role to play in making this instrument. Like one single specialization can never make out the complete instrument. But imagine, this is so mature, and the process of manufacturing it is so mature that you can sell a commoditized hardware for paper microscope. Yes, Prakash Labs thing. So imagine that one. That is something like you just need to buy a lens which costs you 10 rupees in India. Like we are the world's largest lens manufacturer, by the way. So it's just 10 rupees over there, and then the rest is just paper, art paper, chart paper, on which you do drawing, engineering drawing, this kind of thing, and you can make microscopes. So the process over the years, since 1600s, has made it so great. So if you look in simple terms, what happens over there is that you have a lens, you solve the lens equation, and then the physical realization of the lens equation is what you are looking at over there. So the shorter is the distance between the lens and the object, the shorter will also be the distance between the lens and your eye, which is where the virtual image is formed over there. But then the closer and closer you come in, the more and more is the size of whatever is the image which is getting projected, which essentially means that I am growing in my appearance. So it's called as a magnification over there. So I can see the image more clear, I can see things more bigger, and because I can see things more bigger, so I can spot more closely located or more fine differences, and that's essentially what we call as resolution. And the first principle of resolution, which you had studied somewhere in electrical sciences, you have a subject called as measurements. Measurement instruments, measurements and electronic instruments, and then one thing is taught, which is like resolution, sensitivity, specificity. Three things. Eventually later on, like sensitivity, specificity, everybody does in machine learning as well. And then by the time people do it in machine learning, everybody forgets what you were taught in measurements. But the origin was always in measurements. So resolution is basically the distance between two closest points which can be discriminated. This is the simplest term of resolution, and we are going to stick to it. So 10 megapixel sensor on a camera is not the resolution of your camera. That is just sensor grain size. The resolution of your camera is going to be something in millimeter inverse, or lines per inch or dots per inch. If you have something quoted down in dpi, that is the resolution. So how many dots per inch can be discriminated when they are the closest thing which are placed. So this is the story about what we do in the digital space to enable that. Now, typically, like in an optical field, what you do is you can get magnification by these kind of devices which are called as compound lenses. So it's an array of multiple lenses together which can give you a higher magnification factor, so that you don't have distortions with the curvature of the lens. You have multiple thin lenses placed stacked inside over there, and you can get down a total magnification coming out. The issue is that manufacturing this whole thing with the precision so that you have an aligned optical axis, nothing changes over there, is a huge engineering problem, and they cost a lot. That is what increases the cost of the device. And the point is, there is also another associated issue. The associated issue is that the more is the magnification, the smaller is the area coverage over there. So you will have to take multiple images in order to cover the whole thing under a higher magnification, which means that it's more amount of time. So imagine that you are shooting this whole photograph under a magnified view. So in order to cover all the people inside this room on a magnified view, you will obviously get a better resolution, but then you have to take more number of images, which means more number of shots, which means more amount of time which is getting taken over there. So in terms of say diagnostic services which are going to do this, it means that the time the patient has to wait to get access to a report is going to become larger and larger. And all of you know, so when the path lab tells you that come back after 2 days and then take your report, how irritated you are. Everybody is irritated because we are in the age of smartphones and apps which just run on a click. So if I have given my blood now, then even before the guy pulls out the syringe, I should have my report over there. That's my general expectation. So that's my general expectation, may not be your expectation. So how do we really go and achieve that? So this is the story about what was the biggest bottleneck in this piece of the puzzle and how we ended up solving this in a very cost effective way. So associated with that is another fact which is known as physical limits of resolution. Now what does that mean is that this lens over there is not when you recover from them. The lesser the number of things, you will have always these jitters. Okay, that whole thing is what is called as the band limiting property. Okay, and in a physical space, that band limiting property is what translates to the aperture of the lens. The smaller is the aperture, the lesser is the resolution, because you will have this kind of an earring disc pattern coming down over there. That's why you would see that the photograph on a 10 megapixel sensor which you shoot with your these smartphones is still a bit hazy, whereas the photograph which got shot on a DSLR camera of 10 megapixel, that is much more clear. It was still 10 megapixels in both the cases, but the clarity was achieved because of these optical limits. So in case of your smartphone sensor, the lens is smaller, so you have a wider point spread function over there. In case of that, you have a smaller point spread function because the lens and the aperture is much bigger. The sensor, imagine in your DSLR, the sensor is this big. The lens itself is like this big over there, which is like you can fit down roughly about 200 lenses of your smartphone camera inside that one single lens. Is that big? So this is definitely a limit, and you have to play around something around this limit itself in order to solve it. Well, that limit also has another counterpart, which is a boon, which is called as the focal depth. So, like, have you actually put the things under a microscope and seen that when you did the practical session? Or you have a practical session later on for microscope? So you look through the so there was that whole issue of focusing, and then when you move the stage, then again the focusing shifts over there. You will have to refocus everything. Okay, that whole thing happens because the thickness of the tissue is lesser than this focal depth over here. So the higher the magnification, the higher is the numerical aperture, and the lower is the focal depth. So if your tissue is thicker than that, you will never have the whole tissue in focus. Plus, when you are preparing it over there, it's like papad. So if you dry roast a papad, it will tilt. So the same thing happens to this tissue because it is dry. It does not remain like a flat paper. It basically crumbles up and down. So what you want is that whatever is the depth of that crumbling, the distance between the crest and the trough over there, that should fit within this focal depth. If it fits within the focal depth, then every time whatever you move, you will be able to see everything in focus. But in general, that will not be the case. The focal depth is going to vary, and that also decides what should be the thickness of the tissue section which you are cutting. So if you are cutting a, say, 5 micron or something like 7, 10 microns, I mean, most lab technologies can cut at 10 microns precisely. 3 microns, 5 microns is like, they need at least 10 years of an experience to be really good at cutting at those levels of a section.
And the cover slip also determines the thickness of the...
No, cover slip does not. Cover slip is something which affects this, the point spread function. It will never determine anything on that. No. The cover slip is a transparent thing. So what the cover slip does is, for photons, if you are looking at nonlinear photonics, then it will just be having additional diffraction. It's just an additional refractive, diffractive media which adds on to the thickness of the point spread function. Because I never focus on the cover slip. Cover slip thickness, because the thinner it is, the lesser is the effect of diffraction. That is the point. But it does not impact anything within that focal depth. So in fact, if you move that focal plane up and down, you can also focus on the cover slip and see impurities in the cover slip as well. Funny part, the cost of the cover slip is more than the cost of the slide. Do you know that? So if you go to some local path labs, they don't put a cover slip. So if they do a blood smear, you would see that they would take 2 smears and then one on the other sandwich, because that is cheaper than putting a cover slip on top of it. So now, from all of those, today what we are looking into is this kind of digital scanners. So what they do is like this. You prepare the slides, but then you don't need to sit in front of a microscope and do all of these adjustments. So this is like places like, say, Dr. Labs, path labs, which a single center will do 10,000 slides in a day. How will you do 10,000 slides in a day? How many pathologists you need to position at that center in order to just manually scan and do through it? It's never humanly possible. But like today you have these Apollo 24/7, then Tata 1mg, then PathKind treatment labs who will just come to you at the call of a phone or from an app, and then the DMLT guy comes to you and takes your blood smear, and the next, like in 6-8 hours, you get your report on your phone, on your WhatsApp as a PDF over there, and it's a complete NAVL's accredited report which comes out. How do you do that? Because you have these kind of devices, these kind of scanners. So pathologists no more sit under a microscope to look into it. They look into computer screens. They play it like a game. There are gamified engines in order to do pathology as of today. There are pre-screening and everything available. But there is a problem. This thing is from Hamamatsu, a Japanese company. You know what is the cost of that one single scanner? Rough guesses. It is costlier than an MRI machine. 10 crores. How many can you afford in India? You go to a hospital, the hospitals will generally look at that and say that buy more MRI machines, 1.5 Tesla machines, get every patient to do an MR. If you ask me, I would say like, actually don't do a pre-can pathology, because at least like nobody is, that's a completely non-invasive procedure. I put you inside an MR. Except for you will get irritated with all of that boom, 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 pop, 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 all of that sound which comes from within your body when you put you inside an MR. If you don't turn paranoid as a result of that, then the best way of diagnosing is I put you inside an MR, provided I know like where is the region to look into it, and then if we create, there are the whole set of research going on. Bossel Gates is being accelerated around with that, and on creating like permanent magnet flow field MRs and getting them focal coils for specific MRI applications as well. So that's not my part of the story. That's in scenario, I don't know, scenario 3, I think, where I'm going to say something around that. Then how do you really solve this part of the riddle? You need to make scanners which have to be low cost. Companies in India have become excellent in doing that. So we have companies in India which make scanners for under 10 lakhs. Whole slide scanners with an scanning efficiency rivaling anything what an Hamamatsu can do. So Hamamatsu will take you typically about 20 minutes to scan a single slide. These guys take under 4 minutes to scan a single slide. Under 4 minutes. The beauty, there is a generative model which is sitting inside, which allows it to upscale to a super resolution factor so that you can use a lower magnification lens, which means that you have a higher focal depth, which means that you don't have to refocus for every single part of it. You can now put down thick sections and you have a wider area of coverage. We just put down one simple thing, a generative model. Sounds very interesting. And then you know, in order to run a single query on ChatGPT, how many kilowatts of energy is consumed? How much? When you ask a question to ChatGPT, how many kilowatt hour of energy is consumed? One query is roughly 0.2 units of electricity. 200 watt hour. Grid price 2 rupees. Every query you push onto ChatGPT is 2 rupees. Now imagine how much of greenhouse gases you are emitting, how much of global warming. The single root cause of all global warming is computer science. You know why? Because the single device which is 100% efficient thermal heater. So, which is that one machine which is 100% efficiency thermal heater? Think. 100% efficiency thermal heater is a computer. It takes electrical energy. What is the only form of energy it emits from it? Heat. Information is a byproduct. Some numbers stored somewhere. It was just a snapshot of the memory state over there. That was a byproduct which came out of it. The actual product was heat. 100% efficiency thermal heat. If you get down a B certification, those labels over there, you will always get 5-star plus ratings over there. So even your geyser Next day you need to heat your cup of coffee, put it on the laptop. Actually, I have a student who does that. And he puts it, so we have a Raspberry Pi cluster kept down over there, and this guy actually puts his cup of coffee on the exhaust of that one, and he said, this serves my purpose. I said, but then like, the cluster is there for your federated learning experiments. He said, no, that's the byproduct which is always going to happen. The byproduct thing, I actually got it from him. Like, actually, like, the federated learning library, Federa, which we are building, that is the byproduct which will happen over there. The main product is my cup is hot.
That's why there are so much local objection in putting a data center. There is local objection for that.
Data centers, you cannot avoid them. And currently, what local objection? We have more data centers than anything else. Every single mobile tower has a 40 kilowatt data center. Ever been to a mobile tower? A 40 kilowatt heating just keeps on happening over there persistently. A single, any kind of a mobile tower. If you look into those multi-MSO, multi-service operated connected towers, they can be something close to 1 megawatt. And you can actually put your property in front of one of those dish antennas over there and fry it up. I have colleagues in microwave lab who actually do that. I mean, when we were students, we also used to do the same. I used to go to this guys in the computer vision lab, and beside them was the microwave lab, and then like, you want to have some snack, he's like, hey, wait, no problem, I will heat it up. What, like, he turns on one of the radiation experiments and put the pot over here. Crispy fried, oil-free, most healthy food. Okay, so coming from there, so the whole issue is that you need this at magnification, but then how pathologists look is not at a fixed magnification. They look at a stack of magnification. You would see that they would move the magnification turret. They will look at 5x, they will scout that, they will look at 10x, they will do some organelle level understanding, then they will go to 40x, they will do a tissue matrix understanding, they will go to 100x, they will do a nuclear understanding over there. So you need to have this kind of a stack, is another bigger problem, which in fact brings us to the point of another of my interest areas, which is called as data compression. So these slides, typically a slide image, is going to be gigapixel. So this is roughly about 100 gigapixel is what we are looking at. 100 gigapixel, 8 bits. 100 gigapixel. So 100 gigabyte is a single image. You cannot load. You can never load because you never have enough of memory. So you have to do, so all this in C++ with pointers, you wrote those file fseek and pointers. Actually, this is the practical case where you will have to do that and you will just get a piece of the data over there, and all alignments into block scannings and everything comes into play when you write the actual reader over here. So 800 GB. How many DVDs you require? So the slide, by the way, was this small. 2.5 centimeter by 10 centimeter was the actual slide. How many DVDs did you require to store that?
700 MB.
4.7.
So say roughly 4 GB, and you had 800 GB. 200 DVDs. What is the physical dimension of 200 DVDs?
3 axis chale asbe.
And ever go and tell this problem in the class? Everybody says that digitizing will solve all of our data retention problems. I mean, this is one place where this will not solve. This will create more kind of hardware infrastructure problem. How to keep. So it's like a doctor gives you this option. You take this slide, or I give you the digital. So digital is like you bring a matador tomorrow, and it will bring the digital. Or you get a hard disk in your pocket, then I will give you your digital data. So even a hard disk is bigger than the slide. Is it going to solve? So you can come and say, I will take an SSD and do it. 100 GB SSD, what is the cost of that?
Around 800 to 1000.
I'm not saying about a pen drive.
SSD 256 GB. Oh, sorry.
256 MB.
No, this is 800 GB.
800 GB.
So what is happening? 1000 GB and
10,500 করে আমরা
10,000. Yes. We have 500 GB available.
800 GB cards you get up. Yeah, see,
You are talking about NVMe or SSD, right?
NVMe is.
SSD. The 500 is costing you 2,000 and 1 TB costs you 4,800.
What is the cost of consumable of a glass slide? A glass slide comes for 1.2 rupees. Cover slip comes for 4 rupees. The tissue staining, everything over there combined, this is under 30 rupees.
No, but that is again storage, right? Storage and the data protection is not there, but again warranty and all those things. So that's company will earn, so they do fabrication. So this small chip has the capacity of 1 TB, so that's what initially when they started.
Not looking at it, so it's like think as a customer. You go to a hospital, they tell you you can either take this slide or you give me 6,000 rupees and I will give you a digital copy of this slide. What will you do? Think as a consumer, forget you are an inventor. Think as a customer. What will you do? I will give you slide for free. You already paid for the test. But if you want the digital copy of the data, you will have to pay me additional 6,000 rupees.
Nobody will take.
This is the deluge right now what we are facing. There is a whole set of data compression systems which are being built up right now. You need massive data compression. We are looking at like, is it possible to bring that 800 GB level of data to 800 MB, 100 MB? I can go today and claim like we have technologies which can bring 800 GB of image data to 100. So roughly 4,000x. So compression can bring it to 100 MB.
But that compression, if I do it, is it feasible? Sometimes what happens,
Yes.
the pixels and other
It's
stuff
diagnostically significant, so you can make a diagnostic report of it.
make it, right? That much compression
Yes, you can. Deep
To
learning
the
today
power-
is powerful enough to do that.
can be done. Yeah. To the what 8. So yeah, can be done.
Look at the compression factor. 800 GB
To 800 MB.
to 800 MB means 1,000 times.
1,000 MB.
So
So
to
to
200
the what?
MB
To the
means
what
4.
10?
So 800 GB to 400 to 200 MB means 4,000 times.
So to the what 12? 12. To the what
Think
12?
about it, 4,000 times. You had 8 bits per pixel. Now a pixel is going to take how many bits? 8 divided by 4,000.
So is there any way to vectorizing all these things?
That's what you do in order to get the compression engine running. There is a humongous amount of redundancy in series. Humongous redundancy. So you don't need that. That's why compressions will work always.
Sir,
Yeah.
a single slide, the image is 800 GB. How the hospitals are thinking right now?
They don't store.
They don't store. So if for correlation I need the data,
If you take that slide and
and
you again bring the slide. The thing which you do with Excel. So the point is with Excel films or MR films, you can take everything on a DVD because a DVD is more compact and efficient to take it. But for this one, it's turning out that DVD is not the most impactful and efficient to take it. So you will have to take
so
it.
there is no scope of correlation afterwards.
You no. So if you ever go for say anything to do with possible cancerous or malignancy, they will always give you the slide back and say like keep it, reserve it because later on you might need it. So coming to how we solved it out, so we did it for this company called as Syntuple. It's based out of Bangalore. This is about a product which has sold a lakh units right now over there. A bit older paper from 2019. So what we did is very simple. So you take a low magnification lens over there, something like a 5x or a 10x. You acquire everything over there. You do a 4x super resolution on top of it, not a 4x interpolation. So bilinear or even a bicubic interpolation does not work anyways over here because you are still limited with the frequency limits over there. But the genetic models, which can jointly learn low frequency, high frequency relationships, are what play the trick over here. The moment you can do that, what it means is that between a 40x and a 10x, which is a 4x of a scalar in terms of area. So you will require 4 times lesser number of images to be acquired because the area is scaled up like that, the tile sizes become bigger. So now, which means that because I am reducing by 4 times the number of images which I have to take, the number of, say, time to acquire an image also gets reduced by 4 times. So if earlier I was taking 30 minutes to do it, 30 divided by 4, then I'm going to finish it off in 8 minutes. If I do an 8x scale up, I can finish it off in 4 minutes. If I do a 16x scale up, I can finish it off in 2 minutes. That's the speed up story. So the idea was like this, that you first train a CNN which is called as a super resolution CNN. You have a low resolution image which is that LR. You get something which looks like a super resolved or a high resolution image which we call as a super resolved SR. And you try to compare it with the actual real high resolution image. So we had to build a data set like that. The microscope would go to stop over there, you acquire a high res image, the robotic turret turns, you acquire a low res image. The data acquisition was painful, really painful. Like for acquiring one single slide, it would take us roughly 2 hours. Because you have to do a lot of movements, etc., etc., and do it. But the end result was it was always faster because these movements were reduced to 0. Now, one simple way of looking back into both of them is that you find out a mean square error, which is called as a reconstruction loss in this particular case. Now, the issue turns out that this does not just train the model so efficiently. And the reason for that is that you see a lot of these spaces are basically whites or they're flats. There is no cell or there are a lot of RBCs which basically look flat. They don't have high frequency components over there. There is no textural details. There is no high resolution requirement over there. So the mean square error, which is just an average over there, there won't be an error, so it will just push down my thing to 0. So the lower is my value of the loss to be back propagated, it will not have any impact over there. It will not train the model. Then we found out
When you are talking about super resolution CNN, it's on basis of what parameters that this super resolution CNN is basically.
okay, so the idea is pretty simple. So you take a low res, which would basically mean that you will have a lower matrix size over there, say a 640/480. I want to go to a high res, which is say 4 times of that, which is every axis is double. Well, let's start from 320 to 40, and I want to go to a 4x, which will be a 640/480. Okay. What I would do, my first thing is I will just do a bilinear upsample. It's an interpolation problem, but then when you do it, it looks like a larger image, but then it also appears blurry. The blurry was because I was expecting more frequencies, I am not getting that. Now what I do is, I put down a set of filters which are called as high boost filter. So what it will do, all the low frequencies it will suppress, it will boost up the high frequencies over there. A homomorphic filter is a very simple example over there. But then, there can be different kind of bands which it can boost. There can be band boost filters, there can be differential band boost filters, there can be filter bank. Now a CNN is essentially that filter bank. Where I have 2 things to tune. What is the nature of the filter bank, which is the response function over there, which is guided by what is the set of values being taken by the convolution kernel, right? You know, from very fundamental signal processing. And what is the average value of the filter, which is going to be the magnitude which it is going to boost over there. So these 2 things you end up learning from the data. So the backprop algorithm is what plays the beauty over here of boosting it to the point so that I get my desired result. Now the point is, this will saturate because say 95% of the area is just flat. There is nothing beautiful which is going to happen over there.
So you have to use feed-forward network.
This is a convolutional network. I mean, you write any network, I can always break it down into a feed-forward network. I can assure you. I mean, that is what my derivation says. Everything is eventually just a feed-forward network. There is nothing rocket science inside it. So, now here, what we needed to understand is that there is a bit of textural details if you look into these WBCs over here. Dots, spots, nucleus, and that's what diagnostic relevance over there. We need to be able to retain them and boost them to the best possible extent. But then they are very few in number. So that's where we start playing this game called as a Turing test. So remember a Turing test? Alan Turing, what he said? There was a computer and there was a human who was speaking and there was a third human. If if you fail to understand that whether it was a computer or a human speaking, then you say that a computer has become as intelligent as human. And Turing test till date is not yet successful. That was a summer project in MIT. I think 1942 or 44 something. It was a summer project. Now, the Turing test is what we employ over here. There is a super resolved version. There is a real version. We give it to a discriminator, ask it to find out whether it's able to differentiate between them. If it's not able to differentiate, then we are generating something which is as good as the real one. I mean, the real one I cannot change. Only what I am generating I can change. If my thing looks very similar to real, then I have been able to fool it, which means I have been able to adversarially attack it. So this is a pure to be polynomial. Okay. You can also call it as a Tomcat transform if you want. People from morphology they understood the joke. So now the thing was that the first Turing test was looking at the whole image and making a subjective analysis on the gross region over there. But then you also need to look into every single cell and the ones which are of importance. And here that is WBC. So what we did is we played the Turing test, but now on a regional specific thing. So we took out regions which came down from a mask over here, and there were region proposals created. Now you run a Turing test on that. The same Turing test. And once you finish it off, you basically get an aggregate of these two and pass it down. So now look over here. What we did is the losses, which was this JT2 and the gradient of that nabla JT2, as well as here it was JT1 and nabla JT1, which are updating these two, have also been secretively used to update this CNN over here. And what was it doing? This was updating it with the negative of the gradient, which basically means that while that loss is going down, because I am updating this by the negative of the gradient, I am trying to, with this network is trying to push that loss up. So the Turing test is trying to become better and better in discriminating, and this network is trying to make a fool, trying to make it worse and worse in its ability to discriminate by not influencing the parameters of the Turing test discriminator, but by influencing its own parameters. So everybody in your teenage has always tried to fool your parents and the neighborhood watchdog aunties to sneak out with your special friends. And then the way it has is you would adapt yourself instead of adapting the auntie. It's exactly that is what it is done over here. You can still do it. I mean, at this age, you can do it. I mean, most of us are now in an age where we have to be the neighborhood auntie. And because we came from the place where we knew how we were adversarial attacking, so now we have to be aware of the term that we are also going to get adversarial attacks. This is the fun part, like the wheel keeps on going and down back to you again. So now, all of that put down together, this was the bunch of update rules which was going on over there in a phase-by-phase manner. So if you take it together, this is what comes out as the result. The one on the left is the real. This is a single WBC magnified at 40x equivalent of it. If you do a bicubic interpolation, this is what you get. I am saying a bicubic, not even a bilinear. The order of polynomial, the more and more everybody says that will get better and better. There is a whole hypothesis in super resolution which says that bicubic interpolation is going to break any of the super resolution algorithms. It doesn't mind it. There is a limit to it. It will always underplay into that part. So now, SRNet was one of the available algorithms in the market at that point in time for natural super resolutions. This T1 plus T2 is what we had finally with these two Turing tests. Now if you compare over here, the ability to get these nucleolar, this chromatin clouds inside is what matches with this one. The below one is from a sentinel lymph node biopsy, and then you can clearly spot out like what is the extracellular matrix texture which is present over there, which is one of the crucial markers as far as my colleagues in pathology have told me. That is what is relevant in order to be able to diagnose. So this is where it's working. Now if you ask me like, what was the underlying principle over here? What was it doing? It was actually solving a generative model. What is the likelihood of a high frequency spatial representation to occur with an associated low frequency spatial representation? So if you can model that representation, which is what learning this complicated task. How is the discriminator able to understand? The discriminator is basically learning with a high frequency what should be the low frequency. If it is able to see the low frequency but not that high frequency, now it says that okay, it is not a real thing. This guy figured out that if I have to fool that guy, then I have to generate that high frequency component over there, a special high frequency representation which have textures, spots and all of those things. And it learned to model this joint representation, which is my underlying mathematics for a generative model. And that's how it's solved. So that today sits inside this machine over here. This is 110 lakhs FDA certified fully, cells across the world. And you can see the performance. So these are basically all the, they run a set of classifiers and predictive analytics on top of it. So at 16x, you can see what it comes from. It's still above the, like anything above a 95% similarity to the raw scores are like really acceptable for clinical standards. That's what is there. Now the interesting part, you know what 16x magnification would mean? So if my objective magnification is 40x, I can take an image which is 16 times lesser than that. 40 divided by 16 is 10 by 4, which is 2.5x. What is 2.5x of a magnification? Any idea? You take a simple lens, that magnifying lens, and put it over there. You typically get down a 2x to 5x of a magnification. Which now means that we have built up super resolution algorithms which capability enough that I can take a slide, I put a magnifying lens, I take a camera on top of it and take that image, and from there I can actually get down a pathology scale image. Very fictional. I'm still trying to convince an investor to invest money on this technology. But the moment you can do that, now look into it. The scale of revolution you can bring into democratizing pathology practices. So, if this is made reality, then today that Tata 1mg guy who comes to collect that blood sample from you is going to draw the blood sample. He prepares the air-dried sample slide over there. Next, he's going to pull out his camera, take an image, get that one super resolved, report generated, pushed onto your website. So what you are telling exactly that I want it instant. Like before he pulls out the needle and throws it away, I want the report to come in. Because we solved a physical piece of it. Can I remove the microscope out of the equation over there using an AI technology? If I can remove it out, my biggest reason of why I should take that sample to a center is completely movable. Not very far, I think in the next 5 years we will get solutions in this. But the reason is because like we are working on a draft specification to get an approval for these technologies. So CDESCO is working on that, we'll get it. So I have overshot on the time. Do I get some more time?
Yes, sir, sure.
Sure. So we'll overshoot on the paper reading data.
We want to have time. So,
Okay. So that the paper reading session is not mandatory.
it's mandatory, but this session I think is
Make it
adding something
we
more
have
to
read the
us.
paper.
Yes.
We have not understood this.
Okay, then let us spend time on this one. So next thing is what I'm going to get on diagnosis. Now, there is this whole thing which we need to make it clear. So there is something called as detection. What we saw till now is detection. Okay. They will call it as diagnostic services and everything, but remember a thing, that till that microscopy image there is no diagnosis. That comes in. You would get down a blood test report, you would get a blood biochemistry report, you would get down some X-ray radiology, etc., all reports, and then there is going to be a covering report on top of it, which is the provisional diagnosis. So a provisional diagnosis basically makes use of a lot of these tests, which say this is normal, abnormal, and then finds out over a population of people where these kind of abnormalities were spotted out, that pattern was there. What was the most likely disease which caused this? So that is what is called as diagnosis. Now, it has a very important piece. Let me go through this. Yeah.
One term, it's new to me, learnable hashing. Is it a special algorithm?
I'm coming to it. You know hash codes? SHA, MD5, RSA, all of these, right? Yes. So, it's a class of that thing. Okay. But far superior than. search product by image that uses this. So my lab was the contributor to the world's first consumer search app on this one, which was in Bing way back in 2018. And this is like, we brought it to a more practical use in medical scenarios. Right? So how this whole thing of diagnosis works is like, say you have multiple hospitals where you have these things getting reported. So everybody has their own different kind of detections. Like this is high, that is low, this guy comes with fever, they don't come with fever, so many people reported this, that. And then these hospitals are going to share this information with each other. So that's what is called as a physician working group. Now from there, what they build up is something which is called as an evidence. So what does that evidence do? So in case of hospital A, it may be like you had a certain group of patients who were in this age group and age group, and then you found out that they were presented with certain provisional diagnosis and then certain treatment worked out for them. But for hospital B, there was a different group of people for which a different kind of a treatment worked. Now because it was different, they had a different age group, different weight category, so it was a very different thing which worked out for them. Now the point is, if somebody from that city where hospital B was there, got infected and came down to this city and could get treatment in this particular hospital, these guys don't have an understanding of what was in that particular demographic. They will fail to do it. They need to exchange this information. Now, that's what happens typically for any kind of a diagnostic principle, which is called as an evidence principle. Right? Now, what you're trying to find out is basically this base theorem. What is the probability of a certain treatment or disease to be there, given that I have seen these kind of symptoms over there? That's plain simple terms. Actually, a doctor always solves base theorem inside. That's what is it. A diagnostic physician always has base theorem at the back end. And investigative diagnostician always has a generative model in the back of his mind. You know the difference between these two? There are two kinds of physicians. There is a diagnostician and there is an investigative diagnostician.
So one who does the clinical sense, that is one who does with the help of various kind of investigations, maybe that one is investigative.
So it's like this. So there is a web series called as House MD. How many have watched? House MD. Amazon Prime. Go and watch it. It's a medical thriller detective series. So House is a investigative diagnostician. Very few doctors are in that zone, but they make a lot of money. You know what it is? So some people have some problem which does not fit into a pro forma of general problems which the population presents. So when you have some problem, what do? So if you have a toothache, you will go to a dentist. If you have a high fever, you will go down to a general physician. If you have stomach ache, maybe you go to general physician, or like if you have a history, then you would go to a gastroenterologist. Something of this. You have some problem which is like every time you pluck a hair, your eyes go blind and your feet starts to become warm. Says a problem like this. To whom will you go? Dermatologist, ophthalmologist, neurologist, orthopedic, to whom?
Initially medicine.
You go to general medicine, this guy will say you go home. Take rest, you are tired. So that's where investigative diagnostician comes into play. They try to decipher what was the link between all of them through all medical hypotheses available to the most rare of the rarest things. And when it's deciphering, it's trying to find out the joint occurrence of 2, 3, 4 things together. Here 4 things are happening together. All are happening together, co-occurring. It's not like one is causing the other. So that guy thinks in genetic models. Watch that series, House MD. Like whatever Taken Babu series you have watched out, it's much more thriller than that. Hey, no, this guy does like enormous generative models. Every detective does that same thing because they try to correlate between two things. What is the probability of two, three things to happen together such that even a sequence of things will happen together when they investigate a serial killer incident. They try to find out patterns which will be co-occurring in order to do it. Otherwise, how do they do it? Next time you teach generative model, teach it with web series. Maybe students find it interesting.
Web series mystery.
I haven't seen that one.
No, but good analysis is there actually. He is saying that is some little bit of things. This might be this is my result. So in a single shot.
So my fun part is I like it and go for that whole reason because it does it very comically.
So this guy is also comic mixing.
I should try it out. So now let's look into getting that conditional probability. So you want to find out what is the probability given a certain symptom. Conditional. This is exactly posterior probability. That comes from likelihood, prior evidence. You need to have all of them available. Otherwise you will never be able to solve. Let's look into what you have as a collection of these two hospitals. You go down to different ages to different weight groups. And you observed over a period of time. So these hospital A guys were observing number of people who presented this. So what they found out that in the first 3 days they got in this category. That's what I showed over there. Now on the 4th day there is a patient who comes from this particular age group. So they get from 20 to 40, but a guy who is weighted between 40 and 80, 60 and 80. Interestingly, they had never seen anything like this, which means their evidence was zero. So it's a divide by zero problem. It's unknown, not able to get anything. What does this mean? That it was purely access to proper information which was not letting these guys solve out a Bayes equation. So what we need to solve is not Bayes equation. We need to solve a problem of getting this guy enough of evidence so that he can solve Bayes equation, or arm him with likelihood and prior. The evidence will anyways be computed from likelihood and prior. You know that it is sum total over all possible scenarios of the likelihood and prior dot product.
So here ES is 0 you are mentioning here. Yes, right. So this is a case where age is in between 20 to 40 and weight is in between 6
So
to
the
8.
hospital had never seen such kind of a patient earlier. So in their record, do they have any data? But then today the first patient comes in. I never had a historical data. My data set does not have it.
Yeah, age of 20, weight of 60 is very rare in case of.
But people can be there.
People can be there.
I was in that category, so I know it. Actually, since about 25 years old, I have been consistently 95 to 105 in this range. I mean, that is my normal. That is my normal. I don't have cholesterol, I don't have diabetes, I don't have any lifestyle disorder, but I am clinically classified as obese. I'm borderline chronic obese, which I have been there like for last 15 years. There could be these cases as well. So now the hospital has not seen. What do they do?
The probability cannot be calculated, right?
Yes. So the point is that we have to design efficient techniques by which they can get this estimate done very effectively. So that's where comes, okay, so another set of things is like this. What would also happen is that, say you are looking into multiple kind of symptoms which are getting coming over here, and you are looking into their joint occurrences, and then certain drugs which are given and therapies which are given, and what is the outcome, success rates over there. Now, this creates a very huge hyperspace over there. I am just trying to visualize a hyperspace in a much simpler way, but it's a hyperspace which creates over there. Now, if you need the data to come in, so there are essentially 64 blocks. So you will have to fill up 64 bins over there, which means that a single hospital which is getting one patient coming down every day will need over 2 months in order to have enough of things to fill up everywhere, provided every day they get a unique patient coming down. That is the minimum time required to even get your substantial data. If you are relying only on this hospital. But then if I can search out across all hospitals, I can make it faster. Parallelize the process. Serial versus parallel processes. You do it computer science every time, can we parallelize the process over here in clinical practice? If you want to do that, what will happen is pretty interesting. You can get across multiple hospitals and then see each hospital can have a different kind of a dominant set. Such that you aggregate across all of them, you can get more or less a good understanding. Some which have very few evidences, so wherever you have a non-solid being over here, the evidence is really low. Not zero, but it is near zero. Non-zero, near zero value. And there are some which are in solid filled up colors, that means that that's where we have predominant evidences coming down for certain symptoms. So we can solve out this one. You can at least have a well-informed decision which you can take. Which means that I need to get all of this information extracted from whatever data I have. That brings us to the point of retrieval. So this is actually an information retrieval problem. How many have to work on information retrieval? One. The information retrieval is not a trivial task. Even if you are looking at text information retrieval, that itself is complicated. Now here, what I am going to say is it's information retrieval on image scale. So somebody said an image is worth 1,000 words. And a graph is worth 1,000 images. So a graph is worth how many words?
That depends on pre-processing of the data.
Let's come to it. How many words is a graph worth? A million. 10 to the power of 6. So now we are going to look at a problem which is 10 to the power of 6 times of an information retrieval problem complexity in this context. Now coming to the point, image is set of pixels. Rudimentarily, an X-ray is something like 10 megapixels. 10 million words. 10 million, not words, but say like 16-bit every single point. So 8-bit is a character. So it's 2 bits, 2 characters per pixel, and you had 10 million pixels, so it makes it 2 million characters. So which information retrieval problem were you ever trying to solve where your single string length was 2 million characters? You don't have data structures to in fact like encapsulate that. The longest things can be what? 64 characters, 128 characters, 512 characters. I am telling about 20 million characters. Imagine. Just imagine 20 million characters. What is closest like? Closest to 20 million characters. Agatha Christie's whole volume is 20 million characters. That's the complexity we are looking at right now. So let's make it simpler. So what you want to do is like this, what a doctor wants to do, and that's what they today do. So if you go to any of the corporate hospitals, Apollo, Max, Manipal, Narayana, anytime you go, so you would see the doctor sits in front of a PC. And you tell anything, he is just typing everything. He's trying to use this kind of a system. Every of this corporate hospital has built up this kind of a system, and that's the primary reason why these physicians over there are more impactful in giving that diagnosis and finding out very rare conditions compared to any other guy who is just doing a single doctor clinic. And you would see these single doctor clinics are eventually vanishing. You don't have general physicians in your just corner of the road anymore. Everybody is practicing with corporate hospitals. The reason is because you need access to information which is fueled with this kind of large technologies which can enable it. As a single physician, you cannot even subscribe or get access to those. Because these are private, confidential data. It will never go out in the public. So what he tries to solve is like this. He gets an X-ray, it queries into the system and tries to find out all all similar kind of X-rays, or maybe all similar kind of X-rays, CTs, MRs of the lung which presented a similar kind of a symptom without him typing any symptom. He's not going to type. It's an image-based search. Okay, so in terms of your Amazon app, you took an image and then you can ask it like, with this shirt, so this is the image of a shirt, show me all the trousers which will go complement to this one. This is the image of a chair, tell me which tablecloth should I have on my dining table which complements this one. This kind of queries. He's asking similar set of queries over there to this system, and which is going to find him all images as well as provisional diagnosis with all of those images. What does that equip him? That provisional diagnosis is the data set which creates that base theorem, based on which he is going to give his provisional diagnosis. That out of 1 million images which came back to me of the same organ and same pathology over there, which were presented in say 90,000 images out of 1 million images, presented it to be tuberculosis of the chest of grade 2. He's just going to write that, and that is going to be more accurate than anything else because he's not guessing. It actually says that most people who present with a similar symptom actually have this one. And then he would also find out all people who showed a similar thing did not have that but something else. So there will be a set of tests which will be countering his null hypothesis over here, and he is going to now write down that set of tests and then say, can you go this, I do these additional tests, and I need these additional test results, because if one of those markers figures positive, then he is going to think the other way around. He will rule it out, say that now it belongs to the complement set, I will reduce my search margin and then find out. So access to that information. Now comes the problem. Images, say of the chest, I took an X-ray, I can also have a CT. In either of them, I can have different kind of pathologies which it presents. And this complexity tree just keeps on increasing and increasing and increasing. So now, there can be modality which is X-ray, CT, MR, ultrasound, whatever it is, which organ, which is chest or lungs or lower abdomen or what, and then what is the kind of pathology. Plus on top of it, co-occurring pathologies. I have tuberculosis and emphysema of the lungs. I have tuberculosis and atelectasis of the heart. It's going to be a very complicated problem to solve right now. So, you need to have a mechanism of searching that. It's multilateral search as we call it. So, you have different axes along which you can bias yourself and give priorities, and then search out for similar kind of results. So, how do you do it? So, you need mechanisms by which you can represent this 20 million characters, a single image, into a lower dimensional code, a simple bit vector, as low as 64 bits. And that's what our experiment shows. 64 bits is a good number. So if you do that, what it essentially implies is that if I have a pair of images of a very high dimension, I get it into a 64-bit vector, then comparing between these two is going to be a much simpler task. I just have to compare these two bit vectors. If they are exactly same or somewhat same, and it's a Boolean comparison. So you can use a Hamming distance. Essentially bit by bit XOR, and then you take a summation over all of that. If it's an exact match, your Hamming distance is going to be 0. Much faster to do. Because what you need logical operations. I have 64-bit operatable, addressable memories and logical unit processors in our laptops, right? So two such elements and finding a Hamming distance is one clock cycle of a job. Okay, now let's do how fast this will solve it. So I have a 2.4 gigahertz processor, which means that I can do 2.4 giga, which is 2.4 into 10 to the power of 9 such operations per second. Okay, so if I have a single image which is in a hash code of 64-bit, then I can compare with 2.4 into 10 to the power of 9 such images which I have, or 2.4 billion such images which I have in 1 second. Imagine this. So in lesser than the time it takes to get me a Google search result coming to me over the internet, I can actually find out my similarity. And 2.4 billion, what is the country's population today? What is India's population today? In terms of billion. Can you go of 1.4 billion. So even if I want to compare my X-ray with X-ray of every single person in India, I can actually run that in under a second on my app. This is what we are looking at. So you need to break it down into simpler operations. So this is to make it simpler for you. What is it in terms of number of native mock counts over here? You can take photographs, I don't have any issues. All of this is public domain work. So now, what we need to do is that hash code which I need to generate, which is essentially k length. So this bi is basically this hash code which we are looking at. And for sake of simplicity, we just do a plus minus 1. It just makes some other operations on the gradient computation much more easier. Now, if you want to do this, the point is 20 million characters to 64-bit. This is my transformation. Remember, this is what I am looking at. 20 million characters to 64 bits is the transformation operation. It needs to have certain characteristics which it needs to obey. And those characteristics will have to be modeled by this combined effort of this net F, which is the feature extractor network, and the hashing network, which is an FC, a hash generator. So, the next few slides is going to be a cumulative thing of all of these fixes.
Last two slides. So we're basically calculating the space, having space, right?
Yep.
So and you are trying to find out the deep neural, hash parameters, which can later on compute, or what is the outcome? Just next
Any
slide.
image to a hash code.
But where I will use that hash code?
When you are comparing across the database.
Across the database. So if I put that hash code and compute with all the sets of metrics, it will give me the desired result set. Like I am having sample size, I use a filter and I get that. So can I use it every layer of?
No, I'm not going to get across every layer.
Okay.
So the difference is that the feature which comes out is now going to be a Boolean vector. So look over here. So this is a neural network. This is also a neural network. This Fi, this is real value.
Okay.
Pass it on to a tan hyperbolic.
Yes.
I got it between -1 and +1.
Now why I am giving it means tan hyperbolic and?
Because I want to get something which is limited in the +-1 range.
Okay, that's range. Yeah.
Okay.
Plus, can you use some integration or differentiation here? Means I'm
So
just telling.
I have real valued numbers. I want to very quickly make it limited to my range of +-1. What is the function I want to use? I want to use some sort of a saturation function. But tan hyperbolic is much simpler. Or you can even do a sigmoid, then do a
sigmoid.
you do a sigmoid, and then what you do is basically -0.5 over a sigmoid, and then multiplied on the outside. That will also do the same.
Yes.
So any one of them.
So anything I can do, right?
Yeah. And then what you do on top of it, you put a signal function. Just a sign operator. If the value is less than 0, make it -1. If the value is more than 0, make it +1. I get a Boolean representation. I get a binary representation. A binary representation which is good with a Boolean representation. So now, if you look at it, what it essentially means is that once you're able to get this model done, then what it would do is that given that you have a set of images available with you, you store them in your file system in your ephemeral storage or deep storage. You have raw images. But on the database, what do you store today? I mean, you are going to store a file ID of that. On the database, you never store the whole image. Now, along with the file ID, you can also store a hash code. So if I want to compare two images, I'm never going to use the whole image. I'm just going to compare the two hash codes. And the hash codes I showed you how quick they can. So I can have 2.4 billion images compared in 1 second. That's the speed at which I can do. So now when I get a query image which comes over here, so what I'm going to do is, a query image which comes over here, I will get down the same network, I'm going to generate a hash code corresponding to it. My only job is to compare the distances between them, which is what is given over here, as DH of a pair of hash codes. And provided that all the monotonicity and the relationship is appropriately established in this transformation, then whatever is the set of ordering of the properties between the images, pair of images, will be the set of ordering of properties in the hash codes, between the distance of hash codes itself. So once you are able to solve it, then you can do a retrieval which can be modality, organ and pathology specific. But in order to do that, what you would need is that the hash code which gets generated as B, that needs to be structured. A certain set of bits allocated to understand what is the organ, another set of bits to allocate what is the pathology, another set of bits to identify what is the modality in which it was done. So structuring them. So what I am saying is that BQ is 64 bits. But then how many bits out of BQ is B1Q? How many are B2Q? How many are B3Q? So is it like 20 plus 20 plus 24? Is it 32 plus 30 plus 2? Or is it say 16 plus 16 plus 32? You can have several such combinations. You have to find out this optimal over there. So that's another level of design optimization which you have. And plus on top of it, whatever is that length, that was always coming from a neural network. So that also has to be trained. Look at the design space complexity. One is like the architecture of the neural network itself can change, and the weights of the neural network in every architecture has to be optimized to deflect it. So it's a design space exploration plus a training problem. And within all of this, you also have hyperparameter tuning, which is another set of statistical optimization which will take place. So I'll cut short through this one. This is a more interesting slide to look into it. So what you do is, you essentially have a feature extractor network which is called as an encoder. This is a simple CLNS thing. Out comes over there is a 1024 element array, the real value. That 1024 is essentially this Fi. So you see its real value is 1024 cross 1. Right. That gets into three different networks, net 1, net 2, net 3, which gives you a different length. So each of this is going to give you K1, K2 and K3 number of elements coming over here. That K1, K2, K3 can be this combination 16, 16, 32, 30, 32, 2, 20, 20, 24. These different kind of combinations. And you know how many things you can play around over there. So each of these is trained in order to minimize a certain amount of relationship. So what you know is that you have certain kind of labels, like what was the modality they were coming from, what was the organ which was getting scanned, and what was the provisional diagnosis with each organ. So what you want to see is that in this label space, whatever was the kind of a relationship, if they were from the same modality, then the distance is supposed to be 0. The same should be what should be reflected in at least that part of the distance which is getting calculated. So now, that means that we need to create a loss function which is indicative, a Hamming distance which is indicative of the Jaccard similarity coefficient of the label space over here. So this is a bit of maths we did in order to find out how those properties will be there. And this was manual effort, no auto discovery applied over there. This is like, remember curve fitting problems you used to solve at some point in time? This was practically a curve fitting like procedure which was done in order to figure out how we do. So once you do that, this was by training settings, all the different data sets from multiple sources, the combinations with which we did, and then how we measure finally after all of these are trained. So it's something like this, that you get down two sets of images, what is called as Q, which is a query image, G, which is a gallery image, which is essentially like every X-ray from every single human being, 1.2 billion is what you have in India. Then what you do is, you find out what these codes are. So they will constitute these structured parts of it, and then they will be of similar nature. Now, you can find out whether it's matching exactly the modality, only the modality distance computations, only the organ and only the pathology. Or you can do pair of comparison, like is my modality and organ this combo matching, is my organ and pathology combo matching, is my organ and disease combo, or my modality and disease combo matching, or are all three of them matching. So how are these distances computed? So once you do, you can evaluate them. These are ideal combination we found is 20, 20, 24. So 20 for modality, 20 for organ, and 24 for disease. Then it works out pretty good over there. If you look at these numbers over there, the joint thing over modality, organ, and disease. Look at this last. Ability to retrieve 3 of them with the most contact present. Now you can see where it's going to push it up. It is the joint probability of all 3 things being correct, not just one at a time. That's where it starts making differences. Now, this is the joint space over where the fun starts. Because you asked it to solve a different set of these problems in a split out way. So it was able to cluster features associated with certain of these groups into nearest neighbors. So what you would see is that if you look at this yellow, which is a chest X-ray for pneumonia, you would see it located with a green, which was a chest X-ray for COVID. COVID and pneumonia, they present with similar symptoms. You would see they were looking into a similar kind of pattern. In fact, COVID was a subtype of pneumonia. That's why you saw them coming down. So this is the beauty what these algorithms now start presenting. Now, as a result, what we did is we now equip doctors with efficient methods which can now fetch and provide them evidences just at the click. This was the end result. By what? By learning models which can convert 20 million characters or a complete collection of Agatha Christie novel into 64 bits. So next is, now you know it gets boring, but you have to bear with it. I want to finish this one of the treatment. So this was a thing which we were doing for therapy planning. So this is essentially when you have these nuclear medicine therapies going on, you need to calculate something like what is the penetration coefficient and absorption coefficient of these gamma beams inside the body. And that is associated with
A single question. Like as you are using hash, so it's basically not not reversible.
this is a reversible hash. This is a reversible hash.
Reversible hash.
Yes, you can generate the image back from the hash.
From 64.
I can, yes. I mean, that is not in a publication because that is a patent. That is a patent in writing. I don't disclose any of the results or anything, but you can, and it has a huge implication because right now we are looking at encode and compress in one shot. And imagine this: 20 million bytes, characters, 20 million characters, 20 million bytes converted to 64 bits on just 8 bytes. What is my compression factor?
So this learning hash we were talking about previously. We were talking about that Google, Amazon, you can
Picture search.
Picture search.
Yes.
Is it only about picture search or something else?
Oh, there are several. There are graph-based searches, there are legal history search, people do a lot. All of information retrieval today is moving towards hashes.
So that means the technique can be also classified not only as a dialysis part, but it's a basically lossless compression that also you have proposed.
I am not speaking anything over here.
Is it a complete lossless?
So that is
No, it's not lossless, it's a lossy. It's a lossy, but it's a diagnostically relevant loss of compression. Which means that you can still diagnose it.
With the threshold.
So we have publication on not with the hash code but extreme high density compression. So I tell you for mammograms you can go something like 800 times or 1000 times of a compression factor. We have reported for mammograms roughly about 800x compression factors.
800x?
Yes. Your best of what HGIF gives you on your phone is 160, 170x.
That actually came into my mind. Anyway, we will discuss
160 also is somewhat you have to dream.
No, 160 HGIF gives you. 160x HGIF gives you one. We are saying beyond it. So my nominal, so right now, this is a technology I work on it. I have a company which works on this one. We are building extreme high density compression algorithms, and these are for like multimedia 16K is where it will be in the next 5 years. But 16K, you cannot, like your current, say, home fiber network will not be able to support 16K streaming.
Even 4K also.
It buffers.
Buffers.
You don't get it. You need to have a lease line in order to be able to see streaming 4K.
Even I am having 350 Mbps fiber. That's also buffers.
One of my co-founders, he works from a home office which has a 1 Gbps fiber. So
1080 is okay. Means you can say
no, he has a 1 Gbps fiber. For 4K, he also struggles.
No, I'm saying 1080 is still okay.
1080p we have standard. See, 1080p compression standard exists from 2002. It is so old. HPC was originally designed for 1080p. It has been forced down to 4K, but it cannot really do.
But commercialization was not done in the last.
You did not have content being generated in 4K. Content of 4K is just for generating 4K content you need 35 megapixel sensors. Otherwise you will never go native 4K. So the last part of it is an interesting part. How many of you have been inside an MRI machine? Fortunately. How did you like the experience? So how many times did you just jitter and then the guy was, hey, why are you moving over there? How many times did you do? 5, 6? You felt like really claustrophobic over there. That sound was creating this, the humming in your noise was as if like trying to kill you kind of a feeling. Yes, and then you jittered. And then this guy comes on, hey, why are you jittering? And then
10 minutes.
10 minutes. So the problem is that every time you jitter, whatever data got acquired, that is becomes useless. So it is something like this, that an MR works in the principle in the Fourier domain of sensing. So imagine it like this, that you are solving a Fourier series of representation for any kind of a signal, and you are taking one component, one fundamental frequency, you are tracing a waveform at a time. The complete sine wave of one frequency you are going to trace. Then the next one. So the number of such components, the higher the number of components, the better is the resolution. But you will trace one component at a time, which means that it will take longer if you have larger resolution to be achieved. The same thing happens in an MR. Technically, an MR can give you infinity resolution. You can get down resolution rivaling any optical microscope, electron microscope or anything. It can go up to sub-angstrom levels. It has been demonstrated. Sub-angstrom level, no live thing can be scanned. They had scanned material phantoms, scanned it for 3 months. The MR machine was scanning a thing for 3 months. You get more frequency components, you can always get down higher. So sub-angstrom resolutions have been demonstrated. So the issue over here is, the moment you jittered, all the acquisition which happened till that point in time is useless. It corrupted everything. You will again have to start the process. So it's in your best interest that for 10 minutes you just forget everything and lie over there. Because if you jitter in between, you are going to be again tortured for 10 more minutes. Your torture was there, plus another 10 minutes, it will always be there, until your correct acquisition is done. Okay. So we wanted to come up with a solution to this whole thing, which is called as a missing pulse sequence generation. So if you lose out the data, then one part of your data is gone, so one kind of an image cannot be reconstructed. And that's why they would always make you do it again. So can we not generate that from all the other data points which we have? Because if I know it was a sine wave, then why not we use all of this information of subsampling from sparse sine waves and get a generative model to solve it up? That's exactly what we were trying to do over here. So it's again somewhat similar to that the earlier super resolution network. We just have something called as a film network. So you have a missing sequence, which would mean that the tensor, that particular channel of a tensor is going to be all zeros. You pass it through this, in output you should be able to get out a valid thing. So if you have the real data available, you can always find out a mean square error, which is the basically reconstruction error. And then you can actually employ a Turing-test discriminator over here to see how close is the reconstruction, the reality of that generated model to the actual real case, and solve it with a Turing test. Not getting into much details of that one. Once you are able to do it, then you can get results something like this. So if you look at the bottom, So it's a 4-sequence MR, T1, T2, T1 contrast and flare. And on the top is if that particular sequence was not available, which is like for generating this particular one, I feed the network with only T1 contrast, T2 and flare. And then it is predicting what is the T1 image. In the second case, it's the same thing. So all the other 3 complements are available and one end is predicting. You can see how realistically it's predicting, to the point that it can even predict out clearly your gliomas over here, which otherwise was not coming out. This was a case where we were knocking off a pair of sequences and trying to predict it out as well. That is, out of 4 sequences, I have only 2 available, 2 not available. Out of a set of 4 sequences, I have only 1 available, 3 not available. How is it predicting out? So if you look into it, these models actually learn to generate over there by looking into these latent representations, which is beyond scope of first order physics understanding. This is the physiology physics space which we end up learning over here so that it can keep on generating. So beyond that, we tried this more interesting thing which was more relevant for therapy planning, is you need to find out electron densities. So how much of the gamma rays which go into your body are going to be trapped and how much is just going to pass through over there. So this is typically what is found out from a CT number calculation, which is like when you want to go for radiation therapy, you will again have to be exposed to a pre-radiation CT or at least a CR X-ray over there in order to be able to estimate these ones. Now, our whole hypothesis was, why do you want to give another additional set of? Yes, I mean it's a low dose radiation, but it's an additional radiation. And it's going to take time, it's going to build up an additional cost. You will anyways have done an MR, which was for a planning purpose over there for all the soft tissue locations and the pathologies. Can we not use that MR in order to predict out what is there on the CT scale of it? So this is the cross physics point, because CT works on a different principle, MR works on a different principle. But then the underlying thing what they try to look into is the physics of pathology. So different pathological states will have different atomic constitutions and they will result in different kind of signals on MR as well as on CT. So if I can create a hyperspace which can learn that, then I can get the joint model created, the generative model here. So again, not getting into nitty-gritties, by now you have become expert. By the way, I have been teaching about understanding what is a Turing test. So you can also train your models, plus all of these are there on GitHub, so feel free to just dump it out and do it. You will be able to get this. And this is where, before we go for the break, I will take a test. So this is a surprise test with 2 options available in the MCQ beyond the 5 questions which I have given for the test. So here, you can see these references. So you have the real CT and the synthetic CT which is generated from a T2 MR, and you have those zoomed view, the magnified views over there. So you can see how good is the tracing around with the bone. CT in T2 does not have any reflex, MR in T2 does not have anything to understand a bone in direct sense. It is not sensitive to calcium. Simple principles. MR doesn't show you anything to do with calcium. You can like not discriminate radio opaque soft tissues in case of MR, but still it's able to project it out because of that latent space over there. And in fact, like gas filled structures. And radiation, whether it's going to air or nitrogen or water, X-rays won't get into any bigger kind of an impact. MR will have significant impacts. So now how do you really predict it out over there? Is the question. Now, one is real, another is simulated. How many are supporters of the left, how many are supporters of the right? And your left, your right, not my left and my right. My left is your left.
Real.
Right one is right.
Left.
Real. How many support that left is real? Here, raise your hand. How many support left is real? Raise your hand. 1, 2, 3. How many support right is real? Raise your hand. Awesome. curve structure over there has only flags. And on the MR you did not have that visible. That's why you could not. This was the reference image given. But that is something only I know. It's my model, I will know its weakness. We have fixed it already. The consumer grade deliverable of this one has that. Okay, that's all. So,
But for normal city move isn't table movement only in case of spiral city.
for every city you will have to do, because the gantry over there is what is spinning. You will have to do this whole helical scan, so the pen moves inside that gantry and comes out. Now the point is, if you are doing it with a 128 slice or a 256 slice scanner, then typically like, the 256 slice can cover from your neck up to your abdomen in one shot. And that's why they will just position it once, in one snap it's over and you are. But go to like somewhere where they have a 4 slice city and experience the full movement in 10 minutes and humongous amount of radiation exposure. So these are where you can read more about it, and if you want you can join these NPTEL courses. We just finished the 2025 run for it, but 2026 it's again coming up.
Plus or NPTEL?
These are NPTEL. So if you want to look at the deep learning class, so you can Google upon, you can actually search on YouTube. It's called as AI 6.002. So that's my that's a like one semester when I was teaching in the class, everything was recorded by some enthusiastic guys. So the whole classroom teaching is in that one.
That is also on NPTEL.
No, that is like separately available. So that's the classroom thing in the IIT syllabus.
Can you tell
AI 6.002.
AI 6.6100?
6.002. That is the subject code basically. You can search with that and you will get us to it. But again, that's a bit older, so it might not cover hashing and these things which I have to do. There will be some simpler things. But that has a more rigorous coverage than the NPTEL things which we have. Okay, so that's all. And then this is most of the group, and then some more invited people as well who have been working on these things. And whatever I say is basically these guys teach me. They come up with weird problems and then I have to understand from them, and that's how today I am able to come and do all of these jobs up. That's where I end. Thank you. Any more questions if you are not yet ready?
Any more questions, audience?
Sir.
Very interactive and very good.
I generally try to keep it, otherwise I will sleep. My attention span is very low. My attention span is 11 minutes. After 11 minutes, I get bored. It is slower than a standard teenager's attention span. And I have to keep it interactive, otherwise I will sleep.
Thank you, sir, for your enlightening talk. I think we have heard most wonderful talk I ever heard in my lifetime. It was a very much thank you sir, for such excellent talk to enrich us all. Okay. So and I would like to call upon stage principal sir, our coordinator madam and co-coordinator madam to deliver a small token appreciation to sir. Before that, I would like to tell something about the session.
Okay. Summary of the session.
There are 2-3 points if I see it as a learner, as a teacher, and as a researcher. First of all, the new concepts, some of the new ideas. It's not only the diagnosis, like the idea of compression that came during. So this is actually possibly one of the reasons why you need such kind of FTP so that we can generate ideas. So other than the rich content, the research topics, there are a few other things I think who are the junior teachers or the just started their teaching career, how to teach a subject, that is also one came out from here. So we will touch in more definitely, I'm sure although I know you are extremely busy with handling multinational, multi-million-dollar projects, but still we want your support in such of the institutions so that we can boost up our students. So thank you again.
Pedagogy and art of delivering is by the way, I'm the worst rated teacher across my careers. I'm rated very low for pedagogy. I'm rated high for all weird things like does he engage with students? Yes. Like if you can give 6 out of 5, my students would give a feedback of that as well. But if you rate my ratings in terms of pedagogy are always low.
But engagement is more required today because students, they will not sit in a class nowadays. We used to sit because teacher used to force.
Qualitative feedback has something like he speaks so much on so many things that I figured out that the syllabus content was only 10 minutes out of a 55 minutes lecture.
But students were listening.
He wrote it down.
Sit and listen.
Although you get another certificate from IIT, but this is for one.
Very good.
So now we'll
So I think we conclude the session here. We'll go for lunch. I will be joining sir. Thank you.
Education standard exists from 2002. It is old. HPC was originally designed for 1080p. It has been force fed on to 4K, but it cannot really do.
But commercialization was not done in the last.
You did not have content being generated in 4K. Content of 4K is just for generating 4K content you need 35 megapixel sensors. Otherwise you will never go native 4K. So the last part of it is an interesting part. How many of you have been inside an MRI machine? Fortunate. How did you like the experience? So how many times did you just jitter and then the guy was, hey, why are you moving over there? How many times did you do? 5, 6?
I had a breathing.
You felt like really claustrophobic over there. That sound was creating this, the humming in your noise was as if like trying to kill you kind of a feeling. Yes, and then you jittered. And then this guy comes on, hey, why are you jittering? And then
10 minutes.
10 minutes. So the problem is that every time you jitter, whatever data got acquired, that is becomes useless. So it is something like this, that an MR works in the principle in the Fourier domain of sensing. So imagine it like this, that you are solving a Fourier series of representation for any kind of a signal, and you are taking one component, one fundamental frequency, you are tracing a waveform at a time. The complete sine wave of one frequency you are going to trace. Then the next one. So the number of such components, the higher the number of components, the better is the resolution. But you will trace one component at a time, which means that it will take longer if you have larger resolution to be achieved. The same thing happens in an MR. Technically, an MR can give you infinity resolution. You can get down resolution rivaling any optical microscope, electron microscope or anything. It can go up to sub-angstrom levels. It has been demonstrated. Sub-angstrom level, no live thing can be scanned. They had scanned material phantoms, scanned it for 3 months. The MR machine was scanning a thing for 3 months. You get more frequency components, you can always get down higher. So sub-angstrom resolutions have been demonstrated. So the issue over here is, the moment you jittered, all the acquisition which happened till that point in time is useless. It corrupted everything. You will again have to start the process. So it's in your best interest that for 10 minutes you just forget everything and lie over there. Because if you jitter in between, you are going to be again tortured for 10 more minutes. Your torture was there, plus another 10 minutes, it will always be there, until your correct acquisition is done. Okay. So we wanted to come up with a solution to this whole thing, which is called as a missing pulse sequence generation. So if you lose out the data, then one part of your data is gone, so one kind of an image cannot be reconstructed. And that's why they would always make you do it again. So can we not generate that from all the other data points which we have? Because if I know it was a sine wave, then why not we use all of this information of subsampling from sparse sine waves and get a generative model to solve it up? That's exactly what we were trying to do over here. So it's again somewhat similar to that the earlier super resolution network. You just have something called as a film network. So you have a missing sequence, which would mean that the tensor, that particular channel of a tensor is going to be all zeros. You pass it through this, in output you should be able to get out a valid thing. So if you have the real data available, you can always find out a mean square error, which is the basically reconstruction error. And then you can actually employ a Turing test discriminator over here to see how close is the reconstruction, the reality of that generated model to the actual real case, and solve it with a Turing test. Not getting into much details of that one. Once you are able to do it, then you can get results something like this. So if you look at the bottom, so it's a 4-sequence MR, T1, T2, T1 contrast and clear. And on the top is if that particular sequence was not available, which is like for generating this particular one, I feed the network with only T1 contrast, T2 and flare, and then it is predicting what is the T1 image. In the second case, it's the same thing. So all the other 3 complements are available and one end is predicting. You can see how realistically it's predicting, to the point that it can even predict out clearly your gliomas over here, which otherwise was not coming up. This was a case where we were knocking off a pair of sequences and trying to predict it out as well. That is, out of 4 sequences, I have only 2 available, 2 not available. Out of a set of 4 sequences, I have only 1 available, 3 not available. How is it predicting out? So if you look into it, these models actually learn to generate over there by looking into these latent representations, which is beyond scope of first order physics understanding. This is a physiology physics space which we end up learning over here so that it can keep on generating. So beyond that, we tried this more interesting thing which was more relevant for therapy planning, is you need to find out electron densities. So how much of the gamma rays which go into your body are going to be trapped and how much is just going to pass through over there. So this is typically what is found out from a CT number calculation, which is like when you want to go for radiation therapy, you will again have to be exposed to a pre-radiation CT or at least a CR X-ray over there in order to be able to estimate these ones. Now, our whole hypothesis was, why do you want to give another additional set of? Yes, I mean it's a low dose radiation, but it's an additional radiation, and it's going to take time. It's going to build up an additional cost. You will anyways have done an MR, which was for a planning purpose over there for all the soft tissue locations and the pathologies. Can we not use that MR in order to predict out what is there on the CT scale of it? So this is the cross physics point, because CT works on a different principle, MR works on a different principle. But then the underlying thing what they try to look into is the physics of pathology. So different pathological states will have different atomic constitutions and they will result in different kind of signals on MR as well as on CT. So if I can create a hyperspace which can learn that, then I can get the joint model created, the generative model here. So again, not getting into nitty-gritties, by now you have become expert. By the way, I have been teaching about understanding what is a Turing test. So you can also train your models, plus all of these are there on GitHub, so feel free to just dump it out and do it. You will be able to get this. And this is where, before we go for the break, I will take a test. So this is a surprise test with 2 options available in the MCQ beyond the 5 questions which I have given for the test. So here you can see these references. So you have the real CT and the synthetic CT which is generated from a T2 MR, and you have those zoomed view, the magnified views over there. So you can see how good is the tracing around with the bone. CT in T2 does not have any reflex. MR in T2 does not have anything to understand a bone in direct sense. It is not sensitive to calcium. Simple principles. MR doesn't show you anything to do with calcium. You can like not discriminate radio opaque soft tissues in case of MR, but still it's able to project it out because of that latent space over there. And in fact, like gas filled structures. And radiation, whether it's going to air or nitrogen or water, X-rays won't get into any bigger kind of an impact. MR will have significant impacts. So now how do you really predict it out over there? Is the question. Now, one is real, another is simulated. How many are supporters of the left, how many are supporters some things I know is this is the first generation generator. You want to see where the difference is? This is the bed, the metal bed on which the patient is lying. Over there, it's not able to generate that correctly. You don't have this complete curve structure. If you go and lie down on a CT machine, you would see that the bed of a CT has this curve structure versus if you go and lie on an MR, the MR is not a moving bed. So it does not have that curve structure over there. It has only flats. And on the MR you did not have that visible. That's why you could not. This was the reference image given. And that is something only I know. It's my model, I will know its weakness. We have fixed it already. The consumer grade deliverable of this one has that. Okay, that's all. So,
But the normal CT move isn't table movement, only in case of spiral CT.
for every CT you will have to do, because the gantry over there is what is spinning. You will have to do this whole helical scan. So the bed moves inside that gantry and comes out. Now the point is, if you are doing it with a 128 slice or a 256 slice scanner, then typically like the 256 slice can cover from your neck up to your abdomen in one shot. And that's why they will just position it once, in one snap it's over and you are. But go to like somewhere where they have a 4 slice CT and experience the full movement in 10 minutes and humongous amount of radiation exposure. So these are where you can read more about it, and if you want you can join these NPTEL courses. We just finished the 2025 run for it, but 2026 it's again coming up.
Plus or NPTEL?
These are NPTEL. So if you want to look at the deep learning class, so you can Google upon, you can actually search on YouTube. It's called as AI 6.002. So that's my that's a like one semester when I was teaching in the class, everything was recorded by some enthusiastic guys. So the whole classroom teaching is in that one.
That is also on NPTEL.
No, that is like separately available. So that's the classroom thing in the IIT syllabus.
Can you tell
AI 6.002.
AI 6.6100?
6.6100. That is the subject code basically. You can search with that and you will get us to it. But again, that's a bit older, so it might not cover hashing and these things which I have to do. There will be some simpler things. But that has a more rigorous coverage than the NPTEL things which we have. Okay, so that's all. And then this is most of the group, and then some more invited people as well who have been working on these things. And whatever I say is basically these guys teach me. They come up with weird problems and then I have to understand from them, and that's how today I am able to come and do all of these data. That's where I end. Thank you. Any more questions if you are not yet ready?
Any more questions, audience?
Sir.
Very interactive and very good.
I generally try to keep it, otherwise I will sleep. My attention span is very low. My attention span is 11 minutes. After 11 minutes, I get bored. It is slower than a standard teenager's attention span. And I have to keep it interactive, otherwise I will sleep.
Thank you, sir, for your enlightening talk. I think we have heard most wonderful talk I ever heard in my lifetime. It was a very much thank you sir, for such excellent talk to enrich us all. Okay. So now I'd like to call upon stage Principal Sir, our coordinator madam and co-coordinator madam to deliver a small token appreciation to Sir. Before that, I would like to tell something about the session.
Okay. Summary of the session.
There are 2-3 points if I see it as a learner, as a teacher, and as a researcher. First of all, the the new concepts, some of the new ideas. It's not only the diagnosis, like the idea of compression that came during. So this is actually possibly one of the reasons why we need such kind of FDP, so that we can generate ideas. So other than the rich content, the research topics, there are a few other things I think who are the junior teachers or the just started their teaching career, how to teach a subject, that is also one came out from here. So we will touch in your facility, I'm sure, although I know you are extremely busy with handling multinational, multi-million-dollar projects, but still we want your support in such of the institutions so that we can boost up our students. So thank you again.
Pedagogy and art of delivering is by the way, I'm the worst rated teacher across my colleagues. I'm rated very low for pedagogy. I'm rated high for all weird things, like does he engage with students? Yes, like if you can give 6 out of 5, my students would give a feedback of that as well. But if you rate, my ratings in terms of pedagogy are always low.
But engagement is more required today because students, they will not sit in a class nowadays. We used to sit because teacher used to force.
Qualitative feedback has something like he speaks so much on so many things that I figured out that the syllabus content was only 10 minutes out of a 55 minutes lecture.
But students were listening.
He wrote it down.
Sit and listen.
So I think we can put the session here. We'll go for lunch. I will be joining sir at 2.
Selection standard exists from 2002. It is old. HPC was originally designed for 1080p. It has been force fed on to 4K, but it cannot really do.
But commercialization was not done in the last.
You did not have content being generated in 4K. Content of 4K is just generating 4K content. You need 35 megapixel sensors. Otherwise, you will never go 84K. So the last part of it is an interesting part. How many of you have been inside an MRI machine? Fortunate. How did you like the experience? So how many times did you just jitter and then the guy was, hey, why are you moving over there? How many times did you do? 5, 6? You felt like really claustrophobic over there. That sound was creating this. The humming in your noise was as if like trying to kill you kind of a feeling. Yes, and then you jittered. And then this guy comes on, hey, why are you jittering? And then
10 minutes.
10 minutes. So the problem is that every time you jitter, whatever data got acquired, that is becomes useless. So it is something like this, that an MR works in the principle in the Fourier domain of sensing. So imagine it like this, that you are solving a Fourier series of representation for any kind of a signal, and you are taking one component, one fundamental frequency, you are tracing a waveform at a time. The complete sine wave of one frequency you are going to trace. Then the next one. So the number of such components, the higher the number of components, the better is the resolution. But you will trace one component at a time, which means that it will take longer if you have larger resolution to be achieved. The same thing happens in an MR. Technically, an MR can give you infinity resolution. You can get down resolution rivaling any optical microscope, electron microscope or anything. It can go up to sub-angstrom levels. It has been demonstrated. Sub-angstrom level, no live thing can be scanned. They had scanned material phantoms, scanned it for 3 months. The MR machine was scanning a thing for 3 months. To get more frequency components, you can always get down higher. So sub-angstrom resolutions have been demonstrated. So the issue over here is, the moment you jittered, all the acquisition which happened till that point in time is useless. It corrupted everything. You will again have to start the process. So it's in your best interest that for 10 minutes you just forget everything and lie over there. Because if you jitter in between, you are going to be again tortured for 10 more minutes. Your torture was there, plus another 10 minutes, it will always be there, until your correct acquisition is done. Okay. So we wanted to come up with a solution to this whole thing, which is called as a missing pulse sequence generation. So if you lose out a data is one, so one kind of an image cannot be reconstructed. And that's why they would always make you do it again. So can we not generate that from all the other data points which we have? Because if I know it was a sine wave, then why not we use all of this information of subsampling from sparse sine waves and get a generative model to solve it up? That's exactly what we were trying to do over here. So it's again somewhat similar to that the earlier super resolution network. We just have something called as a film network. So you have a missing sequence, which would mean that the tensor, that particular channel of a tensor is going to be all zeros. You pass it through this, in output you should be able to get out a valid thing. So if you have the real data available, you can always find out a mean square error, which is the basically reconstruction error. And then you can actually employ a Turing test discriminator over here to see how close is the reconstruction, the reality of that generated model to the actual real case, and solve it with the Turing test. Not getting into much details of that one. Once you are able to do it, then you can get results something like this. So if you look at the bottom, so it's a 4-sequence MR, T1, T2, T1 contrast and clear. And on the top is if that particular sequence was not available, which is like for generating this particular one, I feed the network with only T1 contrast, T2 and flare, and then it is predicting what is the T1 image. In the second case, it's the same thing. So all the other 3 complements are available and one end is predicting. You can see how realistically it's predicting, to the point that it can even predict out clearly your gliomas over here, which otherwise was not coming up. This was a case where we were knocking off a pair of sequences and trying to predict it out as well. That is, out of 4 sequences, I have only 2 available, 2 not available. Out of a set of 4 sequences, I have only 1 available, 3 not available. How is it predicting out? So if you look into it, these models actually learn to generate over there by looking into these latent representations, which is beyond the scope of first order physics understanding. This is the physiology physics space which we end up learning over here so that it can keep on generating. So beyond that, we tried this